All right, folks, we'll start in 3 minutes, the usual 2-minute academic delay. And those online, welcome, good morning. I'll get things started in a couple of minutes. All right. Can you make me online again? Yeah. I'm ready. Okay. Okay, folks, let's get the day's proceedings underway. First, a quick housekeeping announcement. There was a unintended double booking of this room, so if you're here for the REU program presentations, now is a good time to get off this flight. Otherwise, we'll get... Actually, that's true. This might be more exciting, yes. At least you'll know where you're going. Yes. So,
this is a thumb drive from the splitter for the cell phone here. They're on the ground.
Oh, they're on the ground. Okay, we'll turn them into lost and found. All right. So I won't make any long remarks today. We'll just get going. This is just a continuation from yesterday. This is our third team led by Sam and company. And I'll give it to Sam and let him take it from here.
Thanks. Welcome back. Thanks for the introduction. So we're the sentence representation learning team. I'm not going to make you wait. I want to open with a few numbers that I think really give you the sort of picture of the most important results from this workshop. We wrote about 10,000 lines of Python. We ran about 600 experiments, each of which included training, doing some kind of pre-training and then training task models for at least 9 language understanding tasks. We ate at least 40 boxes of cookies, hence our mascot. This did not include the workshop-sponsored daily cookie hour. There are 23 of us on the team, at least counting people who are active on Slack. 12 of us are in Cookie Monster t-shirts today. We're coming from 10 home institutions. We reported 5 bunny sightings to Slack. We marked 3 days on our team whiteboard calendar with sort of deranged-looking drawings of flaming pickles after hitting debilitating bugs related to the Python pickle function. And we have one participant who decided to join the team immediately after our opening presentation. I won't name names, but this person's been a super great contributor, and we're glad that worked out. Slightly more seriously, what are we actually working on? What are those lines of Python supposed to do? We have some background. So some of you have seen this. This is the condensed version, bears repeating. The sort of technical goal that we're interested in is building a general purpose neural network sentence encoder function, which allows you to get sort of better performance and better data efficiency on language understanding tasks than you'd be able to without it. And we're sort of coming at this goal from 2 angles, and these 2 angles reflect the first and second half of the talk. The first half of the talk is more engineering-oriented work. We're trying to sort of find sort of immediate technical ways that we can improve what's out there in this area and sort of get better results now, or sort of pave the way to get better results in the immediate future. The second half of the talk is oriented more toward analysis, more toward understanding why this problem has turned out to be so hard and so much harder for language than in many other domains, and try to figure out sort of what it will take to make progress in this problem in the longer term. So here's what I'm thinking of when I say general purpose sentence encoder. It's going to be a neural network encoder function that sits between the input text for a model and the sort of the primary model features. It's going to be sort of this extra layer you add on top of your input. It's going to produce some kind of representation for every sentence in your input, and you're going to train only this task-specific model on top. You're going to train a model to just go from these sentence representations to whatever output you want from your task. So classification labels, translation or translation outputs, what have you. This fits into the kind of broader tradition of general purpose representation learning. Probably everyone here is familiar with tools like Word2Vec and GloVe. These are general purpose word representations, and they've been pretty astoundingly successful. They're used in nearly every NLP application and quite a bit outside NLP. In images, we've seen big successes with supervised learning for reusable representations. Sort of these deep elaborated convolutional networks pre-trained on the ImageNet data set extract pretty good image features that you can use for a variety of tasks. On sentences, though, so sentence level features, this has been a problem people have been interested in for quite a few years. We've only started to see what looks like kind of clear progress, what looks like something genuinely useful in the last probably 6 months, more or less even since this sort of the early stage of this workshop started. What would we want a general purpose sentence encoder to capture? This isn't anything we're going to be working on directly. This is just sort of setting up our expectations. We might expect a good representation of a sentence is going to tell you what's in the sentence, sort of what words are there and what order are they in. We don't want to lose any information. It might give you the rough syntactic structure of the sentence, give you some clues to kind of what phrases modify what phrases. It might tell you a little bit about idioms and non-compositional meaning, sort of tell you when to look out for that kind of thing. It might tell you something about connotation and social meaning and sentiment. And it might capture some of the kind of sort of unambiguous semantic information that you get in a semantic parse. But because we're only dealing with neural networks in this context, we'd expect all of this to be encoded in some kind of distributed feature representation, some kind of vector or set of vectors. There's been work on this problem over the last few years that's been focused pretty much entirely on using sort of a single vector as the intermediate representation here, training functions that map sentences to vectors. This includes pieces of work you might have heard of, skip thought, %, and the paragraph vector model. But this hasn't given us things that have actually been all that useful for in the sort of setting that I described here, that have been all that useful as the input layer for some kind of standard language understanding task. And we sort of know why this is. If you look at kind of what's been accomplished in task-specific engineering for most language understanding tasks, we almost never want to build a bottleneck or represent a sentence as a single vector. Tools like attention that allow us to sort of use the sort of linear structure of the sentence in a somewhat adaptive way has turned out to be extremely important. And by adding this sort of sentence to vector bottleneck in our encoder, we're giving up on that. So we'd really rather use something like a sequence of vectors to represent a sentence. And this isn't compromising much. If we use a sequence of vectors, but we at some point need a single vector for a sentence, it's quite straightforward to sort of pool that sequence into a single output. This is just to repeat Ray Mooney's dictum: you can't cram the meaning of a whole bleeping sentence into a single bleeping vector. So in the Mooney compliant models that we're studying, this was going to be something like a deep bidirectional LSTM, and this output is going to be its hidden states, a sequence of vectors. There are sort of three current Mooney compliant models out there. One, sort of the first one in this area is Cove from Salesforce MetaMind. The idea here is you train a bi-LSTM as the encoder half of a machine translation system on English-German, and you sort of remove that encoder and plug it into a variety of other tasks, gets you some improvements in performance. This year, it was sort of discovered, not exactly simultaneously, but roughly at the same time by 3 different major groups that language modeling works quite well as a pre-training task. And this is with OMFIT, Elmo, and a model from OpenAI that doesn't have that pithy name. Talk a little bit about Elmo. It's sort of the elephant in the room. It's kind of what has really gotten what's really sort of popularized this idea in a pretty dramatic way. And it's something we use and build on. It's a part of our best models. Actually, it's the little monster in the room. So to train the Elmo model, to sort of do the pre-training phase here, you train a pair of language models. You train a sort of deep forward language model to predict the words of a sentence from left to right, and you train a deep backward language model to predict from right to left. You don't share any information between these because that would allow you to sort of cheat and predict the word that you just saw. But at test time, you just set them side by side, run them together. So you train these 2 models, you combine them. Then when you actually want to use this, you freeze all of these parameters. You do no further training of your language model or of these parameters, and you drop your task-specific model on top of this using these sort of hidden states from the 2 deep LSTMs where you would have been using your word vectors before. And this gets pretty dramatic improvements in performance. This won a Best Paper Award a couple of months ago at NACL, sort of primarily on the basis of just seeing performance improvements on major tasks at a scale of which we rarely see in NLP. So I'm going to hand it over to Ellie to talk a little bit about what we're going to do.
Yeah, so I'm going to cover kind of the main goals of the workshop, like what was the kind of scientific understanding coming into it and what we were hoping to accomplish. So this is basically just to catch up for everyone very quickly, like if there are people, I guess, from the REU seminar or something, who haven't been following. So kind of the theme of NLP for the past couple years up until the last year has been deep learning is taking over. And this is largely due to the fact that you could drop it into any of our state-of-the-art models and we could see these dramatic improvements. The theme of the conferences in just like this past year or 2 has been trying to say what exactly are these systems learning, and there's been a very consistent trend of negative results. So I can just go through a series of papers that came out in the past 2 years. So some work I had done a couple of years ago on looking at modifier noun composition, some work from last year where they just threw random noise into sentences and showed that like random distractor sentences cause performance to drop quite a bit. So this was on the SQUAD data set. things like lexical entailment. So if you take a sentence and you swap out a word with a very related word, you would often see performance on these inference systems drop by significant amounts. And similarly for things like including negations and antonym pairs. So there's been a pretty reliable trend that it's easy to break these systems that are performing very well on specific tasks by doing kind of gotcha perturbations of the input, and that they very easily break and like lose all of this impressive accuracy that they've gained. So there's been this kind of reality of the world right now that very good task performance doesn't necessarily mean our models are good models of language. And there's some kind of tension between that and that we want to build these general purpose representations of language that perform well on lots of tasks. But that doesn't necessarily mean that representations we're getting out are good representations that we want. So Sam kind of just stated this goal of we want these representations that perform well on lots of tasks. But what we are actually getting at in kind of the bigger picture is we want good representations of language, right? And so our workshop has been focusing on what are different ways that we can define good and how can we try to measure that and build our representations targeted at that. And so on the one hand, there's this generalizability goal. So this is this idea that it should be the case that a representation that works very well on one task will work well on similar tasks. It shouldn't be that the type of language I need for summarization is completely disjoint from the type of language I need for machine translation or information retrieval. It should be the case that language is language and we can share a lot of features of the meaning of language across these very related tasks. And then the other notion is that we want these representations to be kind of linguistically meaningful and capture the types of properties that we think language, a representation of language should capture. So we don't want them to be brittle to these kinds of gotcha examples, and it should be that our representations kind of behave predictably, and they behave in the way that's consistent with how humans expect them to behave. So, so we want them to capture things like sentence structure and negation and synonymy and these types of notions, even if it wasn't explicitly part of the training task. And so we've been looking at two types of ways of evaluating these things on the generalizability. We've been using the GLUE score, which is this benchmark that Alex will talk about after me, that kind of covers a suite of different kind of standard NLP tasks, and the goal there is to do well across all of these different tasks simultaneously so that you're not just optimizing for something like question answering or NLI, but you're doing well across all tasks. And then on the other side, we've been looking at these probing tasks. So here the idea is you're taking some representation that's been trained to do some downstream task, and now you're trying to understand what it contains in terms of like linguistic structure and linguistic knowledge. And there we've been focusing on largely on the notion of using natural language inference as a way of probing, so trying to get sentences to make inferences about pairs of, or systems to make inferences about pairs of sentences. And this is an idea that was introduced in this DNC corpus, which Adam will talk about this afternoon, but we've been doing other similar types of probing as well. And so the kind of overall framing of our workshop is this idea of how are we trying to encode these inductive biases to meet these two goals. One way that people can think about doing this is encoding the inductive bias directly into more and more complex and expressive architectures. So there's a lot of work on that. That's not what we're really focusing on. Instead, we've been focusing on the data side. So the expectation that if you have some fixed architecture, but you're training it to do very different types of tasks, and you're optimizing for very different types of outputs, then you should get different representations. So the same architecture trained to do something like natural language inference, where you're trying to say, does sentence 1 and sentence 2, will contain different types of features about language than something that's trying to do, for example, CCG tagging, which is trying to say, given a sentence, output this kind of structured form of the sentence. And so we're trying to see whether we can use the training setup of the system, the types of tasks it's trained on, the number of tasks it's trained on, to learn a better representation that can then be used without actually altering the architecture at all. And this is based on a lot of prior work that suggests that it does matter. It's appealing to think that you can learn these types of interesting structures through the task design rather than through architecture design, because it does allow you to be a little more passive in exactly what you think the model should contain. You basically say it has to contain whatever requires it to do this task without having to know exactly what that is. And their intuition has been echoed in a lot of recent work. So there was some work about 2 years ago at EMNLP that showed that MT systems capture a lot of syntax better than non-MT systems. There's been work that shows that there are differences in these things like language modeling and MT in terms of how well they capture things like the sentence length, the word content, the word order. And similarly, a recent paper just this past year that showed on a whole battery of experiments that there are these differences in pre-training and the type of surface features that the sentence or the representation captures about the sentence. Most of the focus has been on kind of acceptability and kind of plausibility of the sentence. So does it know when the order of the words are scrambled? Does it know if the order of the clauses are scrambled and things like that? So we've been trying to focus on kind of more applied notions of what these representations capture. So on the one hand, the generalizability aspect, so are these different pre-training tasks lead to representations that generalize better. And then the, I missed one of the bullets that I mentioned on here. But then also these representations change the actual behaviors of the models in terms of the types of inferences that they can draw. So we'll talk about those two later. Very briefly, takeaways before we get into the details. So we have kind of in terms of deliverables and output of the workshop, we have built a really large code base now for learning lots of different representations, trains on all sorts of different tasks with different architectures, and it's fairly modular to switch in and out, so that will be released. And there's been so much manic hacking on this code base. I don't know I've ever seen so many. At one point we had to freeze because our master branch was changing too fast to be able to push a new thing to it. I don't know that's a good thing, but it's like every time you tried to submit, you were out of sync. So, and we've created a lot of data and human annotated data sets. So this probing technique of trying to understand what a model does and doesn't contain requires some fairly carefully designed data sets that allow us to look at different types of linguistic phenomena, and so that will all be released as well. And some kind of high-level takeaways. We've kind of, as Sam mentioned, and has been kind of in agreement with other recent work, language modeling is a really good general purpose pre-training task, or at least it's as good as any of the other tasks we have. But it's not particularly, there's still work to be done, right? So this seems to be the best we can currently do, but it's not quite satisfying, so that's kind of the negative result. And we do see that there are differences between tasks, and it tends to be task dependent, which is a little frustrating from the point of view of a general purpose representation standpoint, but I think future work will be on how to try to figure out what pre-trained tasks help which tasks, and if you can kind of integrate that into your training in a more productive way. And then on the probing side, we did see a lot of differences between models. So the pre-training does lead models to encode different types of inductive biases that do lead to different behavior. But then, again, in the deep dives this afternoon, most of those differences seem to be driven by more heuristic knowledge that the models are learning rather than like deeper structural knowledge. So they're still quite brittle. They're just brittle in different ways. All right, I'll give it over to Alex to talk about the glue benchmark. What? Oh. Here's an outline. I didn't realize that. Okay, I guess I'll go through. Okay, so this is an outline for what the first section will be. So Alex will talk about the glue benchmark and what the metric is. Patrick will introduce the model, so we've all been using a common architecture to train all of our different tasks and probe for them. And then Sam will talk about kind of the highlights of this first section, so generalizability, what are differences in the experiments we saw in terms of how well they perform on glue. And then Jan will talk about learning curves and data volumes. Shuning will talk about multitask learning and weighting scheduling, so how to combine different tasks with very different size training sets in an efficient way. Berlin will talk about the idea of pre-training during, or attention during pre-training. Raghu will talk about Reddit, or more specifically about different loss functions for doing pairwise classification tasks and what leads to better sentence representations. Yinghui will talk about language modeling, and Edward and Catherine, both, or maybe just Catherine, will talk about MT.
Great, so hopefully we've convinced you that learning general purpose sentence encoders is a useful and interesting thing to do. There's still a question of how do we know if a sentence encoder is really general purpose? How do we quantify that? How do we compare different methods for doing so? If you look at the literature, there hasn't really been a clear answer. There's been kind of a consensus that the community has converged upon that we should evaluate on downstream tasks in order to really test the generalizability of different methods. But if you look at the results tables from work as recent as early this year or late last year, the tasks that they're evaluating on tend to vary pretty significantly between different works, and they tend not to compare with one another, so it's difficult to draw conclusions between different methods and really tell what's working. So for the purpose of the workshop, we chose to use GLUE, which stands for the General Language Understanding Evaluation, which, full disclosure, Sam and I were heavily involved with creating this past spring. GLUE bills itself as an open-ended competition and evaluation platform for sentence representation learning models, which sounds nice, but what exactly does that mean? The key part of GLUE is a benchmark of 9 sentence understanding tasks that are built on existing data that varies pretty widely in the difficulty of the task, the amount of training data per task, the train-test similarity, and the genre and style of the data that we're drawing from. All the tasks are classification or regression on sentences or sentence pairs, but beyond that, there's no restriction on the type of model that can be evaluated with GLUE. We have a Kaggle-style evaluation platform with private test data and an online leaderboard with an aggregate single metric. So these are the 9 tasks, including GLUE. You can see that we have tasks with pretty significant variation in the amount of training data. So the smallest task is WNLI at the bottom, which has only 600 training examples, but it goes as high as 400,000 with MNLI and QQD. In the test column, bold numbers are tasks for which we have private test data. We also have significant variation in the amount of test examples. And you can't tell from this table, but the tasks have varying degrees of train test distribution elements. And as promised, we have variation along the domain that the tasks were pretty significant domain difference in the data we're drawing from. So there's formal sources such as Wikipedia and news, and also less formal sources such as social media questions, online reviews, etc. I'm going to super briefly run down a subset of all the tasks so that when we're mentioning these tasks in the next 100 slides or so, you know what we're talking about. The corpus of linguistic acceptability came out this spring, and the task is to make acceptability judgments on strings of English words, i.e., is this string of English words a valid grammatical English sentence? These examples are all drawn from linguistic articles and textbooks, and there's a bit of a train test mismatch in that a subset of the test set is drawn from sources and topics that weren't seen in training data. The core question pairs data set is a paraphrase detection task. Each example is a pair of question titles from the social question answering site Quora, and the task is to determine if they can be answered by the same question, i.e. are they paraphrased or not. And we were really fortunate to work with Quora to get a private test set for this. The multi-genre natural language inference corpus came out last spring and centers around the task of natural language inference, which generally is the task of, given a premise and a hypothesis, determine if the premise entails, contradicts, or is neutral with respect to the hypothesis. The MNLI corpus in particular draws from 5 pretty diverse written and spoken genres, which includes government reports, fiction, personal letters. And again, there's a train test mismatch in that half of the dev and test sets are drawn from sources that weren't seen during training data. And probably the most interesting task, including GLUE, is the Winograd Schema Challenge, which we cast as NLI, and we call WNLI, which is the really small task at the bottom. The Winograd Schema Challenge is a notoriously difficult co-reference resolution task where each example consists of some text snippet with a pronoun and multiple possible entities that the pronoun can refer to. And the data set was manually constructed such that there are no superficial cues that models can exploit to get really high performance. And again, we worked with the corpus creators to get a new private test set. So that was like 4 of the 9 tasks. Each of them has their own evaluation metric, which is usually accuracy or F1, but for some tasks is the correlation. And we also compute a aggregate score by averaging performance across tasks, and we call that the glue score. So I'll briefly talk about the state of the art on Glue, which is due to OpenAI. So the approach of their model is very similar to Elmo in that they're doing language modeling. There's some key differences in that they're using a transformer architecture, which you can see on the left. The transformer architecture is not recurrent, so they use multiple stacked layers of self-attention. Their model is trained on running text rather than sentences in isolation, which Elmo is trained on, which means that they were training on essentially entire books. And unlike Elmo, they fine-tuned their model per task rather than just having per task scalars that Elmo has. So this is generally helpful, but as we'll see, kind of hurts on some of the data core tasks. But the results they get are pretty promising. They get 4% absolute improvement on the Glue score. So this was the state of the leaderboard at the start of the workshop. They get pretty robust, they're the top row here. They get pretty robust improvements on 6 of the 9 tasks. But like we alluded to on the smaller tasks like RTE and WNLI, they actually do worse than the baseline. And how we actually use Glue, all of our models are fine-tuned on Glue, but for some of the models, we train exclusively on the Glue training data. We wanted to avoid overfitting to test, so all of our model selection and hyperparameter tuning is done on Dev. And then we take our best model each week and submit it to the website and validate our test.
Hi, I'm Patrick, and I'll talk about our model. So our experimental setup consists of 3 phases. We have a pre-training phase, during which we train an encoder, which is on pre-trained tasks, which is supposed to give us our shared sentence representation. And then we have a task training phase where we take a target task and we train a model after freezing the parameters for the sentence encoder. And finally, we evaluate for each task, there's a task-specific metric or evaluation. And so for that, we obviously freeze all the weights and just make predictions. So graphically, it looks kind of like this, where we take the input sentence, and then we encode that with some word encoding. And then during pre-training, all of the parameters up here can be changed. But then when we go to task training and target a specific task, we freeze the sentence encoding and only train on the target task model. So for the word encodings, we use Elmo, or we also don't use Elmo sometimes. But the idea here is this is a fixed set of weights that are used as input into our pre-training layer. So this is used, we build on top of Elmo. And for the sentence encoder, we tried RNNs and just no encoder at all, so just directly use Elmo. But we also tried the transformer and didn't get great results there. And we also, as Berlin will mention later, we did investigate whether we want attention in the sentence encoder. We also add a skip connection between the word encoding, the output of the word encoding layer and the input to the task model. This is just to give more information to the task model about the original input sentence. And I'll also talk a bit more about a closer look into the Elmo layer weights and how we might want to vary that per task or keep it shared for all the tasks. First, I want to say something about our code base. So as Sam mentioned, we have a lot of code in our code base, and it's a single common toolkit. So this will be made public soon. And this single toolkit's general purpose for pre-training, for task-specific training, and for evaluating, and it's sentence representations, and it's really easy to add new tasks to this toolkit. So we've used over 70 tasks already, and it's just really convenient to do all of this in with one framework. So now let's take a closer look at Elmo, as I promised. So in the Elmo architecture, we have the input sentence that gets passed in and trained with a forward and backwards language model with multiple layers. And the output of the sentence, the encoding, is a linear combination of the layers determined by some scalars, gamma and s. And so in the original paper, these scalars are supposed to be dependent on the task. And so this motivates our thinking that in our model, during the task training phase, we don't actually want to, we want to think whether do we actually want to share the weights across all the tasks for this, these gamma and S during the skip connection, or do we want to train those weights per task? And so we tried both variants on several pre-trained tasks from Glue, including a pre-trained task on all of Glue, multitask training, and we find that using per task weights does much better generally across the board on different settings of dropout and across all 4 tasks. So as a result, we adopted the per task Elmo weights for our model.
All right, now I'm going to do what I actually promised and sort of give you the pile of numbers, sort of summarizing what we accomplished on the more engineering side of the project. Here are the experiments we ran. We started with what we're calling the BIE, the big initial experiment. Here we sort of divided and conquered. Pretty much everyone on the team was implementing at least a couple of tasks for which we had some evidence they might give you a sort of really good or at least a distinctive pre-training signal we might be able to use. And we sort of ran all of these either with Elmo. We're using Elmo as the input during pre-training to try to sort of build something on top of it, or without Elmo, in which case we used the same character level sort of word handling as Elmo, but removed the sort of language model trained layers. And this included all of our tasks, but language modeling and translation, which took longer to build out. Spent plenty of time after that on the engineering side, debugging, fixing up the architecture, finding better data sets, finding better ways to preprocess those data sets, and building out those larger tasks. And then we, last Friday, launched the sort of big final experiment of taking sort of the cleaned up version of all of the tasks that showed any promise in the initial experiment and running those in a sort of bigger, slower setup with somewhat more careful controls. So here are our results. I want to show you like kind of one big table that summarizes everything, but isn't really possible. Our results table takes about a minute to load on a good browser with nothing else running. This is showing about 6%. It's cropped on both axes. So instead, you're going to see little excerpts from our results, both in the next few slides and throughout the next hour. So here's the proof that we did something. Here are our numbers going up, sort of dev and test set on scores on Glue. Unfortunately, we're starting to suspect that as of the last 2 weeks, we introduced a bug into the code path that sends predictions to the evaluation server. Our test set numbers have not made sense in the last couple of rounds. We're looking into that, but with DevSet, we've both by sort of finding better tasks, finding better data sets, finding better methods, been able to sort of get pretty good improvements. Here's some context. This was the best. This was the sort of best number on Glue on the test set at the start of the workshop. This was also one of these models that sort of combines Elmo with additional trainings. This was Elmo plus training a sort of shared encoder on all 9 of the tasks in Glue. We're able to beat that pretty quickly. And this is the best reported score overall, this language model from OpenAI. One thing we're pretty proud of is that at least judging by the dev set, we're at least getting close to this score. And we're using vastly fewer resources to get there. So by sort of doing, choosing the right task, choosing the right model, choosing the right training strategies, we're able to get pretty close to this performance in about 3 days of training on a decent GPU. This result took 8 months of GPU time, and that's to get the shared model. Then to get the task-specific model potentially takes additional days of GPU time for each task. So Elmo is hard to beat. We sort of took advantage of Elmo. We incorporated it as an ingredient in many of our models, but that did turn out to be necessary. We weren't able to find anything that we could train in a reasonable amount of time that was a complete replacement. So none of our experiments that did not use this Elmo language model encoder were able to beat any of the experiments that did use it. And we're able to reproduce and sort of generalize some of the very strong results that have been seen with Elmo. We got error reductions of more than 25% on 3 of our tasks, 3 of our sort of medium to small data tasks. We did find, though, interestingly, that Elmo is not always helpful. It was consistently harmful by a small margin, maybe a point or so, on the semantic textual similarity task. And there were a couple other tasks where it was just on the borderline of potentially being harmful. So it seems like Elmo, sort of summarizing some results in advance, is pretty good at getting sort of more syntactic local properties of sentences, and can actually be harmful if what you want is a sort of summary of the topic of the sentence, what it's about. So we found that Elmo is nearly impossible to beat. We couldn't beat it, so if you can't beat him, join him. We did find that additional pre-training on top of Elmo is helpful, and we're able to get error reductions of at least 10% on 4 of our tasks with further pre-training. We have a somewhat unusual baseline that will come up in a lot of these experiments that I want to go through briefly. Our baseline is essentially to do pre-training on a task with 0 examples. So our full model has some kind of word handling layer, which might include Elmo, and then a shared encoder, and then a bunch of task-specific models. Our main baseline is simply not training that shared encoder. We randomly initialize it with a good LSTM initialization and leave it there. And this turns out to work quite well. These sort of randomly initialized LSTMs are pretty good at propagating through local information, so they're not very lossy. And they do a good job of giving you kind of local context information. There's been other work that's looked at this kind of model. They work surprisingly well. And this random LSTM does at least 10 points better than simply doing a bag of words style model.
So can I just ask a clarification to make sure I understand it? So when you say you do this with Elmo, do you mean that the input to this by LSTM encoder is the concatenation of the 3 levels of Elmo?
Almost, yes. So the input to the encoder is the Elmo output. We are following the Elmo paper's recommendation and doing this trick of taking a linear combination of the 3 layers of Elmo.
Oh, right, not a concatenation.
Yeah.
Yeah.
But yes, so Elmo, we even though we are also training a sort of input model, we're using Elmo in the standard way as the replacement for our word embeddings.
And this, including the by LSTM, does better than just using the Elmo output directly?
Yes. So with Elmo, this baseline isn't that hard to beat. Sorry, without Elmo, if we're just taking sort of character-based word features and feeding them to this LSTM, we found about 20 or 30 of our pre-training tasks were able to get above this baseline, depending on exactly what you're measuring. Once we add Elmo, this baseline is actually quite strong, and we were only able to find 5 models that significantly exceeded this baseline, and plenty of models actually, I think, disrupted the nice properties of the random initialization and made the model do worse than it would have otherwise. So before we get into sort of the tasks that worked, we spent quite a bit of time on sort of parsing and tagging tasks. These did seem to teach you something interesting about language. What they taught you did not turn out to be particularly useful for any of our target tasks. So we sort of dropped these from our final experiment. Spent a lot of time on image caption matching. Again, this was teaching something sort of identifiable and interesting, but that thing turned out not to be what we needed to solve these language understanding problems. Ditto for a sort of alternative version of natural language inference in this sense. So here's sort of maybe one of the simplest summaries we can make of our results, which is sort of what tasks worked well on Glue. So these are sorted by how well we're able to do on Glue without Elmo for each pre-training task, and we're showing the results with and without Elmo everywhere that we have them. So sort of matching what we know from the success of Elmo, pre-training on language modeling is the best pre-training source that we have, at least without Elmo. There are good reasons you can't combine this with Elmo, but that was sort of reliably our best pre-training approach. The next one, this is somewhat unusual category. These results are a little bit harder to read, but with doing multitask learning on all the tasks in Glue. And then several sort of larger language understanding tasks do well. Textual entailment, a large sentiment data set, and translation do decently. And then disk sent is a sort of an alternate version of language modeling, a classification-based way of using unlabeled data for classification. And again, sort of many of our models were able to beat the random baseline without Elmo. That's the lower dotted line. Looking at this upper dotted line, we only had 5 models that beat that baseline by any margin. Multitask learning on Glue did well. textual entailment did well, and translation did well. And Quora question pairs somewhat. So does pre-training help? Here we're actually using a somewhat different baseline, but trying to, I think, ask this question in as intuitive a way as we can. Here we're comparing the single task version of these models that has no shared encoder, no Elmo. We simply use the same model architecture and train it entirely for each task with a little bit of light tuning to make sure we're not overfitting too terribly. And we do decently. We get 25%, we get 20% error reductions on I think 4 or 5 of these tasks and 10% error reductions on all of them. So this is, I think, for me, the most surprising view of these results, which is looking at all the experiments in our big final experiment, what is the correlation between the performances of the different tasks in Glue? So if I tell you how well some pre-training task allowed us to do on COLA, this acceptability task, can you predict how well it's going to do on RTE, this textual entailment task? And a lot of these correlations are quite low. So to start off with, here's the sort of correlation with the overall Glue metric. How much does the performance of a particular task rise and fall with Glue? First, I'll say that WNLI, it's a real task. The labels are all correct, and it is anti-correlated with everything interesting we've looked at. This is this deliberately adversarial task that's sort of trying to foil statistical cues. The better our models are, for the kinds of models we study, the better they get at these trivial statistical cues that WNLI is meant to foil, and the worse we get. STS benchmark is weakly correlated with Glue because it is harmed by Elmo, and so Elmo generally sort of improves Glue score quite a bit, hurts STS score. So that gives us a somewhat odd result there. We have a lot of fairly low correlations, sort of among the pre-training tasks that do well. Different pre-training tasks help different target tasks with a surprising degree of variation. But it's not all crazy. Our 3 kind of data-rich sentence pair understanding problems, the Quora question pair paraphrase task, the sort of question-answer matching task, and textual entailment are all fairly strongly correlated. So that's kind of a summary of our results. Unless there are any questions here, I'll hand it over to Jan to talk about how these things vary with data quantity. Yeah.
So when you take a correlation, what is if you were to graph a scatter plot of the thing you're correlating, what would the points be? What would each point be?
Each point is a sort of piece of an experiment where we pre-train on a task that is, sorry, how do I frame this?
Is the number of points the same as the number of pre-training tests?
Yes, the number of points is the same as the number of pre-training tests.
So the reason I'm confused by this is I thought that your general mechanism was to train on like 8 pre-training tasks at once, and so every point would be a subset of tasks rather than a single task.
No, you're right. It's a subset of tasks. Most of the experiments that we're reporting are single task pre-training. They're partially because things are still running, partially because we were actually focusing primarily on single task pre-training. Yeah, most of our experiments are single task. There are a few points that contributed to this that were multitask pre-training. But each experiment here. Yep.
You mentioned that you use the standard combination of the Elmo layers. Did you try different versions and they didn't work, or?
We haven't, no. So the one thing that we tried was the sort of easy to implement trivial version of this, which is simply not tuning those weights. So taking a sort of flat combination of the 3 input layers. We were able to do somewhat better by doing this per task tuning they recommend. But we didn't explore that in too much detail beyond that.
One quick thing is, so you have fixed your model for all the sentence pair tasks. Is there any expectation that you will see different correlation numbers for different model families?
That's a good question. We haven't dived into that too closely. But yeah, I think we do see a little bit of clustering by model family, sort of MNLI, QNLI, QQP, these large tasks. They all use, the task-specific models for these are all these fairly large attention-based models. For sort of, though not all of these correlations can be explained by task similarity. For example, STS also uses the same kind of model as these tasks, and the correlations there are pretty weak.
Okay, so I will speak about learning curves for the general purpose encoder and for the task-specific models. And for people who are not here last week and who don't know the concept, the idea of learning curves is that you take your training set, you split it to different sizes, and then you train your model with these different sizes, and you see how the generalization error changes. And we are using it as a tool to see how much you would benefit if you would collect more data for different tasks. So there are some previous theoretical and empirical results which suggests that the learning curves follow a parallel trend, and that the parallel exponent is not dependent on the model size and other hyperparameters. It is mainly dependent on the task itself. So we test these results, and we are studying two questions with these learning curves. The first question is how much we would benefit if we would collect more data for pre-training the encoder. And the second question is how much, or if the second question is if we already have a pre-trained encoder, how much data do we need to train the task-specific models? So here is the first plot is for the general purpose encoder, and we have three different tasks: SST, which is sentiment analysis type of task, QQB, which is question answering, and DISCSENT, which is prediction of discourse markers. And we see that overall we are doing it for models which are using Elmo and which are not using Elmo. And we see that overall the models which are using Elmo are doing better on every fraction of the data set. And if we are training only on, we are starting from 1,000 examples. So if we are training on 1,000 examples, when using Elmo, we are getting already good accuracy or score. And the score is not very much dependent on the task itself, whereas for the non-Elmo models, the score is very much dependent on the task itself. The other thing we can see is that if we would collect more examples for this DISCSENT, we would not gain much, but we would gain probably if we would collect more examples for SST. And last interesting bit here is that when we use Elmo, the SST gives us the overall best accuracy, but when we are not using Elmo, the SST gives us the worst accuracy. So we see that these things interact in non-trivial ways. And the second type of learning curves are done for the task-specific models. So the idea is that we take the already pre-trained encoder and we train the task-specific model on different sizes of the training set. Unfortunately, we are still waiting for the other experiments to finish. So this was done only with randomly initialized encoder, which is using Elmo and one which is not using Elmo. And so every plot here corresponds to one task-specific model. And what we can see even now is that except the first plot, which is for Cola, when we are training on few examples, we are doing much worse with Elmo than without Elmo, which is not the case when we are training on the full data set. So this goes against our intuition, because we thought that if we already have good representation, it should be fine to train on few examples to already get a good score, and that the learning curve should be shallow, which is exactly the opposite here. Yeah, so this is all from me now, and Shuning will present about our learning, multitask learning setup.
Hi, I'm Shuning. I'm going to talk about the multitask learning on Blue. So the goal of multitask learning is to learn a shared representation across many tasks. And in our setting, we have many target tasks, and it's 9. So instead of only care about the performance of one task. We care about improving the performance of all tasks. So the challenge is, since the task has different size and difficulty, how can we efficiently train them and avoid overfitting or underfitting? So there are two approaches to address this question: scheduling and loss scaling. So first I will talk about scheduling. In multitask optimization, we're using alternating mini batch, and in each batch we have single task. So the question here is, how do we choose tasks for each batch? A straightforward way would be doing random sampling. And since we care about the size of task, so we do random sampling with weighted probability. And more specifically, we have different ways of doing weighting: uniform, proportional, inverse, softmax, power. So they just do a simple transformation on the task size and calculate the probability. So to refresh your memory, here is a plot of the task size on log scale. And the smallest task has 600, and the largest has 0.4 million. So if we're doing uniform, they will have all the same probability. And inverse, the smallest task would have highest probability. And proportional, the large task would have high probability. This is a result. This is an evaluation result of all those strategies. So from bottom up, the general trend is the score is increasing, and inverse has the worst performance, and we can notice that power 0.75 has the best, and also proportional is good. So the question here is, does this trend generalize to other task combinations? Since here we are training on 9 blue tasks. The answer would be in the next slide. Those are 3 subsets of blue: C1, C2, and C3. So we train on those subsets and evaluate on those subsets. This is the macro average. So the conclusion here is the red bar seems to be the high all the time, except in the first case it is very close to uniform. That's because in the first cluster, those 2 tasks have similar size. So we can conclude that power 0.75 is generally doing the best. We can trust it. So beyond random sampling, we also try to do active sampling. More specifically, we're using multi-arm bandit. So we hope the program can learn as training goes and also assign probability to different tasks dynamically. So here is the agent, and those arms are different tasks. So but the result shows this bandit behave very close to uniform. So we think something is wrong, but so that's left for future exploration. And second, loss scaling. So the objective function is the linear combination of individual loss. The question is, how do we decide the weight for each task? And again, we can do weighting on the task size. And more interestingly, we want to see what would happen if we combine both loss scaling and weighted sampling. So we tried 16 combination with inverse uniform power and proportional. And the result here is the power sampling with uniform scaling is best. And in general, it seems loss scaling is not really helping. So we conjecture that's because the weighted sampling is already doing loss scaling implicitly, so we don't need to do explicit loss scaling anymore. That would be redundant. To summarize, the first conclusion is weighted random sampling is working, and especially the power 0.75 and proportional is good. And second, loss scaling is ineffective. So for future work, we will do statistical tests to verify the significance of the sampling strategy. And second, we want to improve the bandit algorithm. And most importantly, right now we are doing multitask training on glue, and we want to do multitask training on pre-training tasks like language modeling and machine translation, and then transfer to glue in the future. That's all.
Thanks for shooting it. If you have a question.
This is really nice. I like the detail you put into exploring when it doesn't work. That's some problems. When you sample a mini batch, you are alternating between different tasks. Did you try to explore sampling a mini batch with many different task data within it at the same time? So instead of only doing a batch of MNLI, you do proportional weight in the batch of MNLI samples and semantic textual similarity examples and vinaigrette schema examples. And if you did try that, do you think it would be useful to do that?
So I didn't try it, and from my perspective, I think it will, maybe it will behave similar to like do the weighting between batches instead of inside the batch. But I don't really know the answer. Can you try?
No, we didn't try either, and I hope you might have. Thank you.
All right. Good morning, everybody. My name is Berlin, and today I'm going to talk to you about one of the projects that I'm involved in, which seeks to understand the effect of attention in pre-training. So typically, attention is perceived as something that can be helpful, especially in tasks such as machine translation, where there is a large body of empirical evidence showing that using attention actually helps with performance. But in our setup, we suspect that using attention might not be the best thing. Our intuition is that using attention can decrease what the encoder's representation captures by taking some of the pressures away from the encoders. In other words, using attention can allow the decoder to be too powerful as a decoder. To understand this intuition better, I'd like to draw an analogy to the autoencoders. And on this slide, you can see that there's this general setup of an autoencoder. You see that if the size of this hidden layer here is too large, namely it's more than 4 circles, then nothing's stopping this setup from learning a very trivial mapping such as the identity mapping, which is undesirable if our goal is to learn some low-dimensional representation of the input space that captures some interesting structural information. So just as we don't want the hidden size of the hidden layer here to be too small. We don't want the decoder to be too powerful, which just means that we don't want the decoder to be able to look at what parts of the input sentence to focus on. So to understand this, to see whether this intuition is valid or not, we make some explicit comparison across a pre-trained model with or without attentions. And we consider tasks such as MNLI, QNLI, QQP, embedded data sets, and translation data sets. And also we do the translation data set also for seek-to-seek models. So here is some results without Elmo. And you see that green bar represent pre-trained model with attention, blue bar represent those without. And generally, you see that the trend here is that in most of the cases, not using attention actually does not hurt the performance that much. In fact, in 5 out of these 7 tasks, using attention actually kind of hurts. And we also incorporate this with the Elmo embedding. We haven't done this for the seek-to-seek model yet. But you can see here we have a similar trend where using attention actually hurts the performance. And the difference here is actually quite large, relatively large in the case of Q and Li. So our main takeaway is that using attention is not necessarily good for performance. In fact, in 8 out of those 12 numbers you see, using attention actually kind of hurts. So as a result, in subsequent experiments, our default configuration is not to use attention for pre-training.
Hello all, I am Raghu. I am going to explain the experiments I have done with the loss functions in different sentence pre-training tasks. So we considered Reddit and English-German translation datasets for these experiments. So on the left side, there is an example for Reddit dataset. On the right side, there is an example for translation dataset. So the model should be able to predict one if the sentence pair is valid, and it should be able to predict 0 if the sentence pair is invalid. And you can see there are so many variations here. The semantically different questions will have different answers. Semantically similar questions will have same answers. So we hope the model will be able to predict, will be able to capture this information based on sentence pairs. So this is how we build a training data set for Reddit. If that is a valid pair, we label it as 1. If that is not a valid pair, we label it as 0. And so this is the bigger picture we are trying to address here. We considered 3 different sentence pair data sets, and we did analysis for classification versus sequence generation thing. And we are still waiting for results on sequence-to-sequence generation. And this is first architecture I considered for classification. So we pass the comments and replies through the sentence encoder, and then do one more fully connected layer on the replies, and then do similarity dot product, and experimented with contrast to loss and cross entropy there. And I'm going to explain, I'm going to show the experiments with the cosine similarity and dot product. So the difference is just a normalization. I'm going to show you whether the normalization affects you or not. And contrast to loss versus cross entropy experiments are also done. So the problem with this architecture is you will lose so much information when you do dot product. So we are trying to address another architecture here. So where we concatenate the representations along with some arithmetic and then do classification. We hope that we will show that this model works much better than this model. So these are some experiments with the similarity based architecture, and you can see that the normalization hurts. The right side results are much better than left side results. That means normalization is hurting there, and also contrast to loss seems to be working better than cross entropy in this case. And yeah, we will consider only contrast loss and dot product for the further experiments. And these are comparison of architectures and experiments with attention also. The left side are the experiments for Reddit. Consistently, when you don't have Elmo, the classification architecture seems to be working better than similarity architecture, thereby concluding that doing dot product, you will lose so much information there. And with Elmo, we don't have conclusive results there. And in the case of machine translation data also, without Elmo, classification architecture seems to be working better than similarity architecture. One mistake we did is we used character level model which was trained on English, which is not correct for English-German data set. So we are going to address that later. So the classifier architecture works consistently better in no Elmo case. That's the conclusion here. And we tried to use much bigger data set for Reddit. And we got improvements over baseline here. Earlier we were not getting any improvements over baseline. Now these results are better than baselines. Yeah, these results are on Reddit and machine translation data. Now I'm going to present another crazy idea we pursued. So we are doing, so there are so many different tasks. For example, here SNLI classification and descent classification. We are doing 3-way classification and 8-way classification. Can we combine both data sets and can we try a single classifier to do classification, to learn sentence representation? So yes, what we did is we recasted each data set to binary classification and then combined the data sets to train a single classifier. So this is, we are thinking in terms of doing another way of multitask learning instead of doing block softmax in the output layer. So the architecture we considered, so this is the architecture for sentence pair classification. So this block is sentence pair encoder, which we used here, and then did recasting to binary classification here. So the results are, so the left side bars will show you descent with the multi-class classification, and the middle is after recasting to binary. It seems for this data set, the recasted descent data set working better than multi-class classification, and the result with the recasted descent plus SNLI seems to be worse than the earlier results, which could be because the same set of sentence pairs may have conflicting labels across the data sets. So that could be one reason why that is not working. And so we are trying to address whether we should combine non-contradicting data sets to do that kind of classification. And these are some more results on the recasted descent and multi-class classification, and then doing jointly both of them. So it seems a little improvement is there when you do jointly. And this is the bigger picture I was trying to address. So I was able to do classification with the Reddit and Wikitext, which is a descent, and English German machine translation data. And Yunghai will explain sequence to sequence model for Wiki. Thank you.
Hello everyone, I'm Yunghai. I'm going to talk about language modeling and pre-training and simulated pre-training tasks using unlabeled data. The question we're interested in is, does LM learn good sentence representations? To answer that, we simply train language models and evaluate the sentence representations on Glue as the evaluation metric. The network we are going to build our language model is following Elmo by LM setup, which is a modified version of a 2-layer bidirectional LLCM where we skip the connection between the forward layer and the backward layer. And what the graph didn't show is that we also have a residual connections between the first layer and the second layer. For the input layer, we stick to Elmo character embeddings, which is consistent with all our other pre-training tasks. I'd like to mention that although we following Elmo network setup, it's implemented within our own code base, so it's not exactly Elmo. There are two data sets that we mainly use in our language modeling. The first one is Wikitext 103, which is a subset of Wikipedia articles. It has around 4 million sentences. It has been used in our other pre-training tasks, such as descent. And the other data set is Billion-Word Benchmark, which is mostly web crawls on news sites. It has around 30 million sentences. It is used in Elmo, so we believe that it's a good data source for building language models and learning representations. So while LM actually worked quite well, as I will show you later in our results session, but one of the drawbacks of this conventional LM setup is that it's hard to incorporate Elmo word embedding because the embedding itself is context dependent. So, but Elmo actually shows good gain in our other pre-training tasks that we try to modify our model setup to get advantage of Elmo. This is one of the ideas that we changed to a sequence-to-sequence model, which is similar as skip thoughts, where given a pair of contiguous sentences, we try to encode the first one and then use it to predict the next sentence. So from this setup, we can actually use Elmo in our sentence encoder, which is the blue part of the network. Also, as Raghu just mentioned, we try to recast the above generation task into a classification task. So here is like given a pair of sentences, we predict that whether they are contiguous sentences or not. With similar network setup, we also try to descend with it. The only difference is that instead of predicting whether two sentences are next to each other, descent predicts the discourse marker between two sentences, which might bring more semantic information into the model. Here comes the experimental results. So the first message we get confirmed from our learning curve experiment is that there is a very nice correlation between perplexity and Google score. So as you can see, with more training data, perplexity drops and Google score increases, which indicates that better LM does generate better sentence representations. It's good to know that we're not working for nothing. While we're improving our language model, we're actually improving our sentence representation. Here is the result on non-Elmo pre-training tasks. So while all our pre-training tasks is above the baseline, language modeling significantly better than all other non-Google pre-training tasks, which indicates that language modeling is a good candidate for transfer learning. But it should be noticed that there's still a gap between our language model and the Elmo and the upper Elmo baseline. We hypothesize that it's because Elmo is training with bigger network and much longer time than our language model. So we think with more tuning on our models, these two numbers will be much closer. Here is we're comparing the Elmo and non-Elmo results. So these four pre-training tasks is our pre-training task with unlabeled data. Actually, they use the same data set, which is Wikitext 103. While the LM don't have the Elmo number, we are still waiting for the Elmo number for our sequence-to-sequence model. But from our previous experience, we expect that the number will be similar as the other two tasks. So the first message comes from this chart is that comparing the light blue bar and the dark blue bar, we can tell that Elmo word embedding has a very positive impact on improving the Google score. And also by comparing sequence-to-sequence model with the other two classification tasks, we can show that they have similar Google score. So we think that maybe choosing classification tasks as in pre-training is not a bad idea because this discriminated model is training much faster than the sequence-to-sequence models. So there's still some ongoing work related to compare different word embeddings, and also we're trying on different data genre, especially within glue data. And also it will be interesting and challenging to keep going to improve our Elmo results on transfer learning with unlabeled data. That's all for me today. So next topic will be on MT.
So Edward and I worked on MTS pre-training. Previous work includes COV and a lot of multilingual training, so which helps produce encoders that are cross-lingual. So we saw this rather shocking paper from ACL, which is suggesting that translation quality and meaning representation of the encoder outputs are actually inversely correlated. Here they're plotting blue with the various architectures against the average Sanjeev score. So Sanjeev is a benchmark similar to blue. It was first published in the InfoSend paper. And so if this is true, if this relationship is true, it would be very, very bad for translation as pre-training. So we wanted to prove this wrong, and we wanted to ask the question of whether it's really to do with attention, because if you look at the attention pre-training results, you really see the negative relationship, whereas with the no attention results, it's not very clear. And also with Sanjeev, they're not using attention in the transfer task. So we wanted to see if we don't use attention in pre-training, or if we use attention and use attention in the transfer task, would there be any difference? Our setup is English, German, English, Russian, a very typical decoder. In case this is interesting to you, we had a lot of difficulty with the seek-to-seek implementation on top of Elmo. So first of all, we had very little memory available, and then even considering that the batch size is 24, our implementation is still extremely slow, about 7 times slower than FairSeek. And it was hard to profile their CUDA blocking calls. And we tried replacing the decoder implementation with other open source PyTorch implementations and variations to PyTorch. One thing that may help is to take the Elmo character model offline with a fixed source vocabulary based on the input data and treat the outputs of the character model as pre-trained word embeddings. It wouldn't be exactly the same setup because now you're not training the character models. These were the results we were able to get, both with and without attention. You can see on English Russian, the glue score is higher without attention. On English German, it's about the same. We did see one trend which is very concerning, which would support the paper, which is that as we are training, both with and without attention, as the validation perplexity is decreasing, the glue score goes up and then down, like very suddenly. Like this corresponds to this. But there's a disclaimer that the difference is only due to one task RTH, which is quite small. So the conclusion is we weren't able to disprove the paper, and non-attention seems to be slightly better for pre-training, but even with the same architecture, better translation may not lead to better glue scores. And this is the opposite conclusion of LLM, where we saw that better LLM was better glue scores. We have many experiments still training, and so we wanted to think about why translation would be bad. And the idea is that this particular data set is too shallow because often you can do well in translation just by copying or learning mappings between source and target words. And this might be too shallow compared to language modeling, which is a much harder task, which only relies on previous words. And one thing we have to do is test the quality of this source data and run a language model on our source data to see how it transfers to. But if you have any ideas, like we would really like to, or especially on like how to test these ideas, we would really like to hear, and we'll update you with the rest of our results.
You have a question?
Yes.
I was really intrigued by this plot of how your translation model seems to reach its better performance and your glue scores just plummet off to the distance. Might it be possible to train your translation model with an extra data set and an extra objective that uses the encoder on your glue tasks to stop the translation encoder from becoming so specialized to the translation task?
Yes, that it's kind of what we're doing because we're evaluating glue on a dev set, and then possibly we could choose the best model.
Okay, but instead of only evaluating glue, could you also train on it from the encoder?
Sure. I think so, but the problem is you can tune to a glue dev set, but like it doesn't generalize to other tests. So like you have to have a dev set for a universal thing to tune to.
Okay, thank you.
I think you have another. Why? I mean, you write bilinear attention. Did you use only that? Is there a reason why you use that?
We have very little memory left.
If that's the case, then you can just use dot product attention. Like it's much more simpler and much more.
Yeah, that's true.
Is there a reason why you use bilinear attention?
It's just kind of standard. I don't know.
I had one comment on your question. I think Catherine sort of took a stab at something, but I think it was one of our very ambitious reach goals to look at, which is how do you do early stopping in settings like this? And it's a very hard problem because evaluating on the dev set we care about requires training all of our glue models. It takes between 20 and 50 hours. So we can't do early stopping by just evaluating on the dev set we care about. All right, time for a break. See you in 15 minutes.
Yeah, what was me guessing?
Well, I was going to imagine something. If everyone has to guess without looking at it.
Okay, that sounds pretty easy.
Okay, ready? Here we go!
Wait, can you tell the advertisers?
How are you doing? Yeah, how you doing? And put us back on. All right, thank you. Okay. All right, guys, let's start.
Okay. So now everyone's gotten a lesson on counting. We're all in. All right. So I'm going to talk about the second aspect of our workshop, which was looking into these representations in terms of what they're capturing as far as linguistic properties that we would expect representations of language to encode. So I'll start with kind of high-level highlights of the general structure of how we organize these probing experiments, and then kind of takeaways from synthesizing across all of the probing experiments, and then each of the students will come up and give a deep dive on their particular models and tests that they were looking at. So again, the kind of goal we're looking at is building these general purpose sentence encoders. And then the real goal we're looking at is trying to build intrinsically good representations of language, which is a pretty high-level ambitious goal. This workshop is really focused on the more subtle question of making sure that these neural sentence encoders are capturing the phenomenon that we expect language representations to capture. So we're focusing on sentences, and particularly on these kind of sequence of vector representations of sentences. And so we were looking at this from kind of two perspectives. The first is this idea of NLI probing. So here you're pre-training a model, you're getting sentence representations, and then you're training a model to do sentence level inference. So this is this task called recognizing textual entailment, or NLI, natural language inference, where you're given some sentence like the dog is in the park, and then you're trying to decide whether or not some hypothesis is true, like the dog is outside, or something like that. And so the assumption is that this is a very general purpose way to represent all kinds of linguistic phenomena that models should be able to make inferences about language, and you can frame a lot of different types of linguistic phenomena in this form as sentence pairs, and then you can test whether models make correct inferences about it. So those are framed as NLI probing, and then we also have work on what we call edge probing, and so this is really looking at the individual vectors within these representations and saying, like, does this encode some notion of part of speech or of semantic rules or something like that. And the kind of thrust behind all of this work is trying to understand what these inductive biases learned in pre-training actually capture, and whether that affects model behavior. Like, is pre-training a useful way to get our models to give more appropriate behavior on various tasks? And if so, where and why and how? I don't know why this happened. So we looked at...
the sentence representations haven't stabilized yet.
Exactly, yes. Yeah, it was meant to be deep and metaphoric like that. So we focused our probing experiments around 5 different models. We actually did consider a couple others, but we weren't able to get them results together in time. So the main pre-training tasks we were looking at were language modeling, natural language inference, syntax, and grounded language modeling. And the reason we chose these different tasks was we thought these were quite orthogonal types of training objectives. So we would expect that if pre-training is leading to very different types of representations, we should be able to see that by looking at these tasks, which are very different. We look at the random encoding baseline, which Sam talked about before. Again, this is a take all the Elmo weights, then a randomly initialized BILSTM, but with no pre-training. And then we have language modeling pre-training. We have natural language inference, which is, again, given this pair of sentences, predict whether the first sentence entails or contradicts the second. We have a syntax, which is a CCG super tagging. So there you get a sentence and you're trying to predict the sequence of CCG tags for the words in the sentence. And then we have a grounded model, which is given a sentence, try to predict the image that corresponds to that sentence. And the model architecture we're using is the same as in the first half, but we're really just focusing on this top sentence. So we do all of the pre-training and then we freeze this, and then we train a logistic regression classifier to do the inference task, because all of our probing will be framed in this inference setting. So you get a pair of sentences and it's a binary classification, yes or no, does the first sentence entail the second? So we need to train a classifier to do something like that, because most of these pre-training tasks don't know how to do that. But we use a very simple, just a logistic regression classifier. So it's really constrained to using the features that are there at the output of pre-training. And the way we designed our tasks was we were trying to be as controlled as possible so we could avoid the kind of lexical priors and other types of things that we often see appearing in these types of evaluation setups. So we designed all of our tasks in this way where we either have a single premise with 2 different hypotheses, one that's entailed, one that's not entailed, or a single hypothesis with 2 premises, one that's entailing it and one that's not entailing it. So here we can make sure that and we've tried to constrain so that these pairs of sentences are kind of minimal pairs. So you're really hoping that if the model is understanding the phenomenon you're probing for, it should get it right in certain cases, and it should understand that it's not, very kind of surface level similar sentence, but one that doesn't capture phenomenon. So easier if you just look at some examples. So these are the set of this is part of the probing tasks that we looked at. So we're looking at all sorts of phenomena. There's this top one is this subsequences. So the notion is trying to say whether a subsequence appearing in a sentence is entailed by that sentence. So you get something like the small boy heard the man did not want to wear bright colors, and you want to say that whether it's entailed that the small boy heard the man. Actually, I flipped the order of those 2. Yeah. So we have this one, which is supposed to be kind of a notion of constituency and syntax as well as entailment. We have work on prepositions, where we're just swapping out individual prepositions in a sentence to change the meaning, to see if models are picking up on these kinds of light words and the correct representations of them. We have work on negation, for looking at inserting explicit negations as well as doing lexical negations, so replacing words with their antonyms. And then we have several tasks that are focused more on kind of grounded type of language, so things like appearance, so like colors, dark versus light, big versus small. Comparison, so things like more than, less than, taller than, smaller than. Quantification examples, so things like all and some, and like no more than, at least as much as, and those kinds of numerical reasoning. Spatial reasoning, so relative position of things left versus right, up versus down. And then verbal complements, which includes like implicative verbs and active verbs. And so you'll hear more about all of these different tasks after I give highlights. And then we also looked at some tasks that are part of this DNC corpus, which was again work prior to JSOL from some of the members of our team, and Adam will talk about this immediately after me. But the idea here was to take a lot of more traditionally studied phenomenon in NLP, so things like named entity recognition and thematic roles, and recast them into this NLI format. So there's a ton of a large data set for each of these phenomena. We focused on 4 here: named entities, factuality, thematic roles, and entity relation, like relation extraction. And they follow a fairly similar format to what we're using, but not exactly paired, so they don't always have this constraint that the premise and the hypothesis appears with two things, but they're fairly balanced and controlled for various lexical pairs. So I'll just cut into some kind of high-level results that are looking across all of the models we look at and across all of the tasks that we look at, and then there will be deep dives on each one. So this plot is showing for all of the models that we care about, and for these different tasks. The black bar is the performance of the random encoder, and then this is performance of the pre-trained model relative to the random encoder. So you can see a pretty intuitive result, actually, that with what we're expecting to see. So pre-training on a task like inference does lead the model to do a better job at capturing things like negation and like implicatives and factives and these kinds of traditionally like inference-y types of tasks. Whereas pre-training on images does capture a lot of phenomena that we expect to be captured better by images, so things like appearances and spatial relations and quantification. And these are kind of raw accuracies where a random guessing baseline would be 50% because of the way we balance the data. So that was a pretty intuitive and satisfying result. And just to answer what I think is an obvious question, this isn't really due to the fact that the pre-training task was giving it more exposure to the vocab. So we actually saw a negative correlation between the percent of the probing task vocab seen in pre-training and the performance, which doesn't make a ton of sense, but it's largely driven by the fact that our language model doesn't do that well, and it had by far the largest training set. So basically, I think if you control the language model, there wasn't really a correlation. So it's not the fact that they're just getting more exposure towards like left versus right, or forget to, or remember to, or whatever. But there seem to be other types of biases that are being built in that aren't explained by vocab. So I think one of probably the most interesting takeaway for me, at least, was this kind of correlations that we saw between these pre-trained tests. So this is aggregating over all of the different probing tasks we looked at, but balancing because they were different sizes. So, so equally weighting all of the different probing tests and saying how often does the prediction on a given sentence pair made by this model agree with the prediction made by this model. So how often are they making exactly the same predictions on individual pairs? And you can see that there's pretty a lot of regularity in this correlation matrix. So like the main thing that jumped out is that there was a lot of systematically similar predictions from the models that were trained on text tasks versus the ones that were not. So like language modeling and NLI and the random encoder, which is then fine-tuned on NLI, tend to make very highly correlated predictions, whereas the grounded model and the CCG model, which are training on a task that's not a text-based task, so images or these kind of logical parses, they also make more correlated predictions, which is not particularly intuitive, except to say that maybe there's something kind of orthogonal between the signal being captured between non-text models and text models. And this does change a lot if you look at different probing tasks. So for example, these the CCG type model behaves more like the text models in the preposition case than in the negation case. And you see a lot of variation across individual probing tasks. So you'll see more results kind of related to this in the follow-up discussions. Another kind of higher level takeaway, so we were very careful in designing these probing sets to try to control for, again, these kind of minimal pairs, because there's been a lot of work on these like gotcha examples where you say like, oh, I took this sentence and I changed one word and then it no longer captures the phenomena. So we want to have these pairs where you expect it to say entailment on one pair and contradiction or non-entailment on a very similar pair. And the degree to which these act as gotcha examples tends to be consistent across all of the models. So this is a loaded chart, so I'll explain. So this first bar is the overall performance of the model on the task. And then the second bar is the model on the, like, it only counts as being correct if it gets both of the examples in the tuple correct, right? So if you say, if you're looking at negations and you get some sentence pair that says like, the cat was in the park, the cat was outside, and you get that right, you get a point for that, and then you say the cat was not in the park, the cat was not outside, and you get that right, you get a point for that. That's probably a bad example. Then you get overall accuracy, but then the second bar is you have these tightly paired examples, and you only get credit if you get both of the ones in the pair right, so you can't exploit one side of the inference. You have to be able to get the kind of controlled inference. And this gray bar is kind of what would be expected if there was no systematic relationship between the two pairs. So basically what you're seeing is that in something like these syntaxy ones, these constituents and negation, it's consistently the case that the model makes, that gets tricked by these gotcha examples. So the performance plummets a lot when you make these minimal changes. Whereas down here on some of our other data sets, there don't seem to be these systematic things. So like it's not recognizing that these pairs are very similar and should be treated similarly. It is treating them kind of independently. The main point that I think is interesting is that this seems to be not model dependent. So if these gotcha examples are tricking the LM model, they're also tricking the CCG model and the grounded model, whereas on these other tests, if the gotcha examples aren't tricking one model, they're not tricking any of the models. So this kind of pre-training does not seem to be affecting this type of robustness in the way we would expect it to. So kind of general themes that will get followed up on in a moment. There are major differences among the pre-training tests that we saw in the kind of just overall performance across probing tests. But as you'll see, a lot of this does seem to be due to differences in the heuristics that are being learned during pre-training, not kind of fundamentally deeper knowledge that's being captured by pre-training. So they're learning different useful heuristics that allow them to perform well, but they're still learning heuristics, and it's easy to, it's still easy to trick them. You just have to trick them in different ways. These tasks that are hard are universally hard, so that's kind of what this previous plot is showing, that if there's kind of easy ways to break one model, that doesn't seem to, it seems to be true across all of these models. It's not like some models are learning much more robust representations. We have some preliminary evidence that the distinction between whether your pre-training task involves text only versus text in some other modality does seem to make a difference. But we only have 4 tasks that we can really compare across, so that would require further work. And it seems that we didn't actually solve NLPs, so that was kind of a disappointing result. Okay, there we go. All right, so here's the lineup. So Adam will come up now and talk about the DNC recast data set and just the notion of recasting to MLI in general, as well as some of his results on those phenomena. And then Tom will come up and talk about this subsequence modeling problem. So does a sentence entail all of its subsequences? Do the models believe that that's true? Najim will talk about negation, explicit versus lexical negation, and where the negation appears, whether it's in the premise or the hypothesis. Roma will talk about grounded representations, so what can we learn from images and what kinds of inferences do those capture or not capture. Alexis will talk about verb complements, so implicative and impactive verbs. And then Ian will talk about this notion of edge probing. So this was a whole separate set that doesn't use NLI probing, but a separate set of experiments that really focused on saying for individual spans within the sentence, what is encoded about the, for example, part of speech syntax and semantic roles of these individual pieces of the sentence. And the goal here, trying to tease apart whether the information is even there. If it's not making inferences based on this information, then is it because the information is not there, or just because it hasn't learned how to harness it? Sam, why didn't you have this problem? I have too many bullet points.
Because his results stabilized.
That's all right.
Thank you, Ali.
Yes.
I really like these linguistic probing tasks. I think they're really, really wisely chosen. Like they're very particularly targeted with respect to like certain like key functional aspects of what we think of are important for these tasks, like these functional words like prepositions for spatial language or connectives. And I think like the word on the street was that when you drop connectives and stuff and try to predict that as a task, like that ended up helping for some of your root scores and stuff. So I'm wondering if it would be worthwhile to think of, I think they're great a posteriori, like things that you can do to analyze how your models perform on these pre-training tasks. But I wonder if you actually use those probing sets, like where you drop these instead of trying to necessarily distinguish between them.
Yeah. So there's like
key pre-training tasks.
So like if we wanted to capture prepositions, we should train a model that's designed to predict prepositions. And then, I mean, I think definitely, but there's kind of a really hard question, which we'll talk about as kind of follow-up questions, which is like, you can't anticipate all the phenomenon you want the model to capture. So to some extent, the point of trying to have pre-training is what pre-training tasks will allow it to just by default get most of the probing things. So maybe prepositions is well motivated as something you would want to explicitly train for, but like you could pick any other, like I'm trying to think of some fairly obscure probing tasks that one might do. Like we talked a bit about metaphor early on and then ended up not pursuing that. That's something that ideally I want like a perfect model language to capture, but like pre-training on metaphor starts to feel more cringe. Or like something like I want it to be able to capture certain types of pragmatic inferences, right? Like if I, like the meaning of a sentence like that one in context, right? Like do I have to pre-train on some very grounded, I mean I like the idea of pre-training on that kind of task, but basically the probing tasks, like you can train for probing tasks and then they will do well in those probing tasks, and that's almost a given, I think. So it's kind of like which things would be like the basis of things we're willing to train on versus which things do we think we should get for free without having to explicitly train for. And I think there's kind of a trade-off there. So to some extent training on like more well-motivated tasks would probably help.
And I'll hit on some of that as well. Kind of talking about like recasting.
There was one more question.
I think was
yeah.
around.
I was just going to ask for questions. I was actually looking at the use of internal tasks.
If you're over, can you yell?
Yeah, using like what was initially used as a program task as a constraint task and see if that includes certain aspects of existing use of such tasks. So if you're interested in
There's like, if you pre-train on the probing task, you would hope that it would improve something other than the probing task as well.
Yeah.
Otherwise,
This is what I mean. Yeah, obviously those are the probing tasks.
Right.
Thank you. Started talking about recasting natural language understanding as natural language inference and what that can do for us. So here we really have this notion that inference is everything, where the goal is to create linguistically targeted natural language inference data sets in order to provide insight into models' capabilities. And we've argued previously that most NLU tasks can be reframed as NLI, and this we refer to as recasting. This is a paper at IJCNLP last year from our group here at Hopkins. And what recasting is, it's converting existing natural language understanding annotations into NLI, ideally with minimal human involvement, and ideally in a programmatic way. And previously we've shown that we've used how one can use recast NLI to evaluate different models. So here we show, and NACA we showed how that can be used to evaluate NMT models. In the setup here, even though this is a very similar setup to what we're doing here, the only reason why I'm putting this picture here specifically, because in a lot of the other diagrams it showed just one sentence, but here we're dealing with two. So what the setup here is, you pre-train your model. Here was NMT, but as we're about to talk about now, it's going to be a lot of different tasks. Then you extract sentence representations from your pre-trained encoders for your NLI tasks, and you use those features, those sentence representations as features to train and test classifiers on each of the recast NLI data sets. So the DNC stands for the Diverse Natural Language Inference Collection, and this is a large-scale collection of recast NLI data sets. It covers 7 different types of semantic phenomena, and we recast 13 existing NLU data sets for those semantic phenomena. And right now, the size of the DNC is almost 600,000 NLI paired examples. And this was joint work done with researchers here, Brown and Rochester, prior to JSALT. But here's the whole list of the different types of semantic phenomena we consider in the DNC. For the purposes of JSALT, we considered 4 of these. So we looked at event factuality and NER, and these are examples of what they look like. So in the first column, you can see the premise or context. Second column is your hypothesis, and the last column is the NLI label, whether it's entailed or not. So the first 2 show examples that require a model to perform factuality. Event factuality is just determining whether an event happened. The bottom examples show NLI examples that test how well a model can perform NLI and the reasonings related to that. The last two from the wide set of the DNC that we consider here are recast verbnet and recast relation extraction. And again, here are examples of that. So the recast verbnet is basically using the roles from propping that are in verbnet. Those are some of the examples. Now I'd like to look at what are the insights that the DNC can provide into these different encoders for different tasks. So basically, the y-axis here represents accuracies, and the x-axis represents what the encoder was, whether this is or what the probing task is, whether it was NER, factuality, verbnet, relation extraction, and the colors represent different encoders that we used, whether we used encoder trained for language modeling, for syntax. The thing I really want to point out here, and lastly, the bar on the right is the majority baseline. So that's how well your model do if it always predict entailed or not entailed on that probing data set. But here I'd like to just briefly touch about the verbnet examples, because we can see that the other probing, basically the encoders perform similarly on the different probing tasks, but we can see a noticeable big difference in verbnet. If we notice that the encoder that performed the best in this probing task was the syntax, it's referring to the CCG parsing. And one reason why we believe this might be the case is that there's a high relationship between syntax and the semantics in verbnet, which is prop bank semantics, because really we sort of know that the semantics in prop bank are very shallow and correlate a lot with syntax. And it is interesting that these results sort of confirm that. Right? Oh, point? Yeah.
So I'll be discussing some work done with Tal Linzin on creating a challenge set for natural language inference. And our motivation begins with the fact that LSTMs are great at discovering statistical regularities in your data and then using those regularities to develop strong heuristics for tackling your task. But the problem with these heuristics is that they usually don't work in all cases, and they might even prevent your model from learning the deeper behavior that you really want it to be learning. So this leads us to wonder, when you train models on natural language inference, are they actually learning to perform inference, or are they more often just developing heuristics based on surface level cues? So to start getting at this question, we focus on one specific heuristic that we think models trained on NLI might be adopting, namely the heuristic of assuming that a sentence entails all possible subsequences of words within that sentence. And the reason we think that a model trained on NLI might adopt this heuristic is because in many cases it does give you the right answer. For example, the sentence, John likes Baltimore a lot, does entail its subsequence, John likes Baltimore. But there are plenty of other cases where the heuristic fails. For example, Alice believes Mary is lying does not entail Alice believes Mary. In fact, it probably means that Alice does not believe Mary. So to test whether our models that were trained on NLI are adopting this heuristic, we create a data set of examples like this one, where the sentence contains some subsequence that is not entailed by the larger sequence. And we then test whether our models think that it's entailed anyway. So here are some initial results at that task. And the chance of performance would be 50%, since the models simply have to choose between two options, either entailment or not entailment. And you can see that regardless of pre-training tasks, all of our models performed well below this chance baseline. But they're not performing at zero, so this makes it natural to wonder, when they do get the examples right, why are they getting them right, and which ones are they getting right? So here are a couple examples that some of our models did label correctly. So for example, some models did correctly say that they heard the tapes are of no importance does not entail they heard the tapes. And some models also correctly said that the young American believed the statistician is not involved does not entail the young American believed the statistician. But if you look closely at these examples, you'll notice that they both have something in common. Namely, they both contain a negation word somewhere in the sentence. And if you looked at our larger data set, you would find that this trend holds for pretty much all the examples that the models are getting right do contain a negation somewhere in them, which suggests that maybe when the models get these examples right, they're getting them right for the wrong reasons. That is, they might be using another heuristic where they basically notice that there's a negation word in the first sentence and not in the second sentence, which they use to assume that there is not an entailment relationship between the two sentences. So to test whether the models are just relying too heavily on the negation in the sentence, we try removing these negation words and then seeing if the models still give the correct labels to those sentences. So to refresh your memory, here are our results from before with the unmodified sentences. And now here we add in the results when we remove those negation words. So as this graph shows, the accuracy plummets to basically 0% when the negation words are removed, which suggests that even in the cases where the models give the correct label, it is for the incorrect reason of basing their decisions entirely on those negation words. So what can we conclude from these results? Well, number one, it's pretty clear that this is a very challenging evaluation set, since pretty much all of our models got basically 0% accuracy on them. But we can also conclude that all of our models seem to be basing at least some of their decisions on unreliable heuristics, whether those heuristics be based on subsequences of the larger sentences or in the presence of negation. So this suggests that to get models to truly learn inference, we might need to augment our training data with harder examples, or perhaps modify the architecture or loss functions to make these heuristics less readily accessible. Any questions? Yeah. No, it does not, because, yeah, so with or without the negation, the correct label is does not entail. Yeah. But the predictions from the model do change, so that's why they flip in accuracy.
How big is the data set?
It's 64 examples, so pretty small. But yeah, we constructed it by sort of merging together sentences from within the MNLI corpus to make sure that it was in domain and only involved dependencies that the models had seen before, et cetera.
Yeah, actually shows that all of the probing data sets are constructed from MNLI sentences so that they're like in domain and have been, the vocab has been seen in the basic relations.
Yeah.
Of the sentences that it gets wrong, in general, what fraction of them are sentences like the ones you've shown that basically have a that implied that is missing?
Good question, yeah. So in the results we showed, all of them are that type, but we are exploring looking at other types of constructions. So for example, you could also have a case like the book on the table is blue does not entail the table is blue, even though the table is blue. So
if we have time, this question is a little high level, so maybe it's better for discussion at the end. How are we on time?
You can throw out the question, then we can answer it at the end.
Yeah.
Because now you've teased it.
So in some sense, maybe these results aren't surprising because the architecture of the networks that are making the inference predictions doesn't look like anything like the good old-fashioned AI systems that actually manipulated propositions. So do we need different architectures in order to solve propositions?
We might. I mean, I think LSTMs could learn this, but I guess not given the training data we've given them. But there has been some work recently on sort of negation with comparative expressions, like John is more happy than Mary and John is less happy than Mary, where given standard MNLI training, the models don't get those cases correctly, but then if you add cases like that to the training data, then they do get it correctly. But there's a good chance that something that has a more nuanced representation like that would do better without having to be given additional examples like that.
Let me ask the question in a different way. So the questions that you have here, I'm not sure whether the examples in your data set are of the easy kind or the hard kind. And by the easy kind, even though they're still hard for the system, they might be easy in the sense that a system that did parsing could get them. On the other hand, there are versions like, I heard the cat and I heard the cat meowing. I heard the cat meowing does imply that I heard the cat.
Right.
Whereas I heard the cat was not involved is different. And it's because meowing, if the cat is meowing, that's different from the cat being involved. The cat meowing is actually producing a sound. The cat being involved is not producing a sound.
Yeah. So we were hoping that this was part of the reason we were looking at exploring pre-training tasks, is there does appear to be like some like notion right now that you can maybe get some of the advantages of what one would get from parsing by pre-training on a task that explicitly requires understanding something about parse structure, and then you don't actually have to parse, but your representation will encode what is needed to make those types of inferences. So we were hoping to see that the CCG model was better at this, and it didn't turn out to be. But it could be that this data set was really hard, and Ian will talk a little bit more. I mean, he doesn't actually talk about the CCG pre-training, but basically like what aspects of things like parse structure are encoded in these representations. So there is some kind of hope that you can do something like auxiliary task training and multitask training, or just pre-training to try to get something that allows you to behave as though you have a parse, even though you don't actually have a parse, right?
So my question was about the things that you couldn't get even by parsing.
Oh, even,
okay. So the problem is inference, long inference chains take more steps.
Yeah.
And the architecture here has a bounded number of steps. You know, you have so many levels. So if you wanted to do something that got the really hard examples, the ones that require reasoning, I wouldn't expect this architecture to do it. And I'm wondering whether the data set that you've constructed is one that finds out, is the system able to mimic parsing, or are you finding out, is the system able to mimic reasoning? I would expect that the architectures that you're looking at would be able to mimic parsing, but I would expect them to fail on any kind of reasoning because they can't do an unbounded number of steps.
Yeah, so these are examples where just getting parsing should be able to give you the right answer, because if you are basing your decisions on a parse tree rather than the linear sequence of words, you really would have no reason to think it was entailed. But it would be a good idea to have some harder examples where simply not being a constituent is no longer means not entailment, like I heard the cat meow. Okay, we'll hand it off to Najim.
Is this actually so I'll talk about negations. So we sometimes want to challenge some sentences like Cookie Monster is big, as one usually does. So there's more than one way to do so. You can say Cookie Monster is big, and if you want to challenge this, you could say Cookie Monster is not big. Or you can say Cookie Monster is small. Or similarly, you can create these sort of like contradiction pairs by saying is not and is, and it's not small and it's not big. So I wanted to ask the question that do models understand the interaction between lexical and explicit negations? So lexical meaning like small versus big, and explicit meaning is not versus is. So I generated some more examples because about like lying on a dirty bed instead of Cookie Monster sentences, because that was in the MMLI data set. So the first sentence is like what was originally in the data set, and I created multiple versions of like logically negated premise and the hypothesis, and this is not an exhaustive list. So we wanted to see whether this did well on sort of like an MMLI task that tries to predict the labels. And the first thing we notice is that raw accuracy generally drops, so the blue bar versus like all the negative versions. So this is kind of boring, but a more interesting thing is that looking at like do models correctly flip their like originally correct judgments? So if they got it right in the first place for the first sentence, do they get it right by flipping their originally correct judgments to another correct judgment? And this sort of shows an interesting pattern because it actually differentiates between different types of pre-training. So random does really badly, and NLI and image-based pre-training tasks seem to do better on explicit negation, whereas other models get like the lexical negations more correctly. So we looked at the distribution of correct answers in the premise and the hypothesis. So like the cases where the negation, either lexical or explicit, was in the premise or in the hypothesis. And the general trend is that like the models are able to pick up like the correct answers more when the negation is in the premise than in the hypothesis. But this is not always the case, because if you have double negations, meaning like both lexical and explicit, the models do substantially better when like the lexical plus explicit negation is in the hypothesis. And also this came up multiple times I was asked this question. So people ask me whether like putting the explicit negation words substantially increase the number of contradiction predictions in general. And like among the models we tested, it was not true. So if you compare the blue bars to all the other bars, sometimes so for the image model you get more contradictions, but all the other models there are more contradiction labels in the original set than the negated set. So that was not what we saw. So to summarize quickly, random is bad and pre-training is somewhat helping models to pick up negation, and there are some interesting qualitative differences in what types of negation models are good at, but no model is amazing, and this is a challenging task, and maybe we should aim to be able to parse sentences like that. It's not the case that it could not be not small. That's it.
So here we want to explore if a visually grounded learning objective allows you to learn good meaning representations for sentences. So this is what our model looks like. Given a sentence, our objective is to visualize it, and that means predict image features. And more detail about our model is we have the same sentence encoder. So this is 1500 dimensional barrel STM, which encodes the sentence. Our image encoder is a pre-trained CNN on ImageNet, so this is ResNet 101, and we want to find the best possible way to map the two representations to each other. Our data, which I'll go into a little bit more in more detail later, is images paired with captions from MS COCO, and these have 550K samples. And we evaluate in the same way on the glue benchmark and on NLI probing data sets. So this is what our data looks like. And here we want to explore what we can actually learn from visual grounding. And it makes sense to think that this kind of data allows you to ground to real-world aspects as opposed to things like metaphor and implicatives. So these are samples from our training data. And the nicest thing about this is that each image is paired with 5 captions. And these 5 captions nicely complement and contrast each other. So for example, in the second one, you can learn that less than half of something possibly means that most of something is gone. Or in the first one, you can see that if there's a motorcycle on the left and there's like a larger number of motorcycles to the right, more means that that quantity is larger than the next one. And we'll go deeper into this with the probing tasks. So these are the things that we want to probe for. So do our models learn about appearance? So do they know that blue is different from green and white is different from red? Do they learn about quantification? So do they know things like the number 28 is not the same as the number 54? Some is not the same as all, but some does not exactly contradict all. Do they learn spatial relations? So do they know that left is different from right and above is different from below, but above is maybe the same as on top of? And do they learn about comparison? So is larger different than smaller and bigger and other things that can be visually compared? And from the results, we can see that the grounded model seems to be doing better than most other models on all the 3 tasks. But I'm going to go deeper into one of them, which is quantification, to see what exactly the model is learning when you look at the meaning representation that it learns. So again, we can see that the model does better. So grounded does better than CCG and NLI and random and all other models that we tested for in our probing test. But let's look explicitly at the categories. So for example, we want to see if the model learns about numbers. We want to know if it can determine relations between sum and all, least and most. Does it know that quarter is less than a half and third is less than a half, third is more than a quarter, and things like that. So within the quantification categories, we can see that the model seems to do specifically well on numbers. So it learns things about numerical reasoning. It seems to learn about sum and all, but not so much about least and most. So let's probe further into the meaning representations and see what the model is learning. And the simplest way to do this is if we look at the grounded space, so once we extract sentence representations from the visually grounded model, and then if we look at sentence representations for text-only models, and we look at how the words are distributed within the 2 spaces, is there a significant semantic shift in the 2 spaces that shows us that the grounded model is learning something significantly different? So for example, if we look at text space and grounded space, we can see that the most similar words, meaning the words that are closest to a word in that space, differ significantly. So for example, we're looking at sum over here. In text space, sum is more similar to things like many, numerous, certain, and so on. And these are all semantically similar words. But in the grounded space, you can see that sum is more similar to few and certain and dozen for some reason. And then much lower down are larger quantities like many, numerous, and various. And like
it's not intuitive to say that one space is better than the other. There is evidence that the grounded model does perform better on quantification tasks. But one thing that we want to probe for further is what exactly it means that there is a shift in the semantic space and what we can do with this with better grounded models. So this is all left for future work, but the grounded models seem to learn more about quantification and spatial relations, even without explicit annotations of bounded boxes. And now Alexis will tell you about the more abstract probing tasks.
Hi, so my name is Alexis, and I'm going to be talking about my work probing for whether models are understanding inferences about verb complements. So in certain contexts, we can infer that a verb's complement is true. So in this example, for the sentence, I remembered to go to the store, it is true that I went to the store, so we should be able to make that inference. But sometimes we can't make an inference that the complement is true. So if I negate the verb remember, then it is not true that I went to the store. If I switch the verb, though, to know, the labels that we predict in each of these contexts changes. So if I say I know that she went to the store, then she went to the store. And if I say I didn't know that she went to the store, then she went to the store is still true. So what we see is that different verbs behave differently under negation. Specifically, know that presupposes the truth of its complement, and remember to does not presuppose the truth, so it's sensitive to negation. There are different categories of verbs that tend to follow patterns of behavior across different contexts. So this is kind of an overwhelming table, but basically what to look at is that the columns are different contexts. The first two are the ones we looked at in the previous slide. And implicative verbs are verbs like remember to that are sensitive to negation. So in the second column where the verb is negated, that's the neg sent, we can't infer that the complement is true. For factive verbs, this is not true. So you can say that the complement is entailed even when the verb is negated. And there are lots of other types of verb behavior over different contexts. Implicative and factive are just two main categories that linguists have given names to. But basically, our high-level question is we want to understand which pre-training configurations, if any, allow models to encode information about the implicativeness or factiveness or otherness of verbs. And this is the same as asking which models correctly predict labels across the four contexts, because we're calling a verb implicative if it predicts implicative labels across these contexts. So the design is an NLI task, took sentences from the MLI train and dev sets and created 4 NLI pairs which correlate with the 4 contexts in the previous slide. And for a given sentence, we collected human annotations across the 4 relevant contexts for whether the complement was entailed, and then categorized them according to those human annotations. So this is accuracy across the NLI pairs in general. Models seem to be doing okay. The MLI example, which is the 4th column, is doing the best. But this doesn't really give information about the question we're interested in, which is how are models doing in terms of predicting labels across the 4 contexts. When we look at accuracy within the verb categories that we're interested in, models are doing worse. So you can see that the highest percentage of accuracy is within the implicative column, and that's the model that was trained on grounded. So here, the purple models are models that were trained with information that wasn't text only. So grounded and CCG had some sort of non-text information. And the orangish models are models that were text only. We see that the text plus models, so the purple models, are better at recognizing true implicatives than the orange models for implicatives. We also see that the text models, so the orange ones, are better at recognizing true factives than the purple models. In fact, none of the purple models actually get any of the factive category verbs correct. And overall, models are categorizing implicatives better than factives. So all the numbers in the first column are higher than all the numbers in the second column. And so we wanted to know why that was, and so I'm just going to talk a little bit about digging into these trends that I did. The first trend, which is that models are categorizing implicatives better than factives across the board, we want to know why that is. And what we realize is that all models are biased towards predicting implicatives no matter what the actual verb behavior is. So this is a plot where the y-axis are the true categories of verbs, and you don't have to read the labels. All you have to know is that the green box is showing where the category is actually implicatives. And the bars are corresponding with the percentage of all predictions that the models made for that category that were implicatives. And so what you see is that all models basically are predicting implicatives across all the categories. And so yes, in the green box, they're getting some of the implicatives right, around 50%. But this is just because they're predicting implicatives for everything. And this bias can be explained by a simple heuristic that Tom talked about earlier, which is that models tend to predict the label not entailment whenever there's a single explicit negation in a hypothesis or a complement, but not in both. So this is the behavior, this is the labels that the heuristic would predict, and they're also equivalent to the implicative labels. So this explains the bias towards predicting implicatives. Second trend is, why are the text-only models, or the models that incorporate non-textual information, better at recognizing true implicative than the text-only models? So that's asking the question, why are the purple models doing better in this category than the text-only models if they're all biased towards predicting implicatives? And specifically, what are text models predicting if not implicatives? And what we see is that text-only models have also learned this bias towards predicting all entailment across categories. So this is a graph now similar to the last graph, but now it's showing percentage of predictions that were just all entailment in all four contexts. What we see is that the orange models are predicting this label, predicting all entailment across all categories. So there's this additional bias that they've sort of learned. And then we're going to talk about this last trend, which is that the text-only models seem to be better at recognizing true factors. Why is this? Is this also due to a similar bias towards predicting factors across all categories? And what we see is that no. So this is a model showing model predictions for factors across the true categories, and the green box is the actual true factor category. And in that model, the orange text-only models are predicting factors, but they're only really doing that in the true category. So they're picking up on something that's unique to factive verbs behavior in factive contexts. So the takeaways are that the models are not doing too well overall, and where they are doing well, this can be attributed to simple heuristics, except maybe that text-only models are learning something true about factors, and future work will be digging even more, figuring out what verbs models are doing better on, etc.
Hi, I'm Ian, and I'm here to talk about this edge probing project that Ellie mentioned earlier, sort of the other half of the probing efforts. So I'm going to be giving this presentation, but this was joint work with a number of other people on our team, particularly Patrick, Berlin, Adam, Najim, and Tom, who helped process some of the data and do some of the analysis for this. So you mentioned we're calling this edge probing, and the idea here is that we want to understand how well these sentence representations are encoding structural information, and particularly because before end-to-end neural networks kind of steamrolled everything, and we decided we can just cram everything into biology layers and let them learn whatever reasoning we need. We used to build things like parse trees and build structures on top of that, and we would understand explicitly how the parts of the sentence relate to each other and use that to perform reasoning. So we want to try to go back to this and build up this understanding of what's happening in these continuous representations using the existing structural annotations that we know are useful and encode information that's relevant to these tasks. So we've got lots of different layers of this. You might take a sentence from, say, Hontonotes that's got all these different layers of annotation, and you can get different formalisms. You can get dependency edges from one token to another, and you can look at what is the nature of this syntactic relation. You can have semantic role edges from a predicate to argument, and you can ask, is this an agent, a theme, instrument, patient, so on. And you can even look at single spans and say, is this a named entity of a particular type, or is this a noun phrase, verb phrase? Or you can look at two tokens and say, are these two spans co-referent with each other? So these are all getting at different types of information, kind of at different levels of the syntactic semantic hierarchy. And so broadly, the question to answer, how is contextual information encoded at the token level? How do these embeddings, so going beyond some of the stuff that's been done in the literature where people look at, say, part-of-speech tags and probing these representations, we want to look at specifically interested in relations between two tokens. How well are these encoders that we're learning representing information across the sentence and using it to relate different parts to each other? And then also try to tease apart, are different representations qualitatively different? Are they encoding information that might be useful? So we're not going to totally answer this question yet, but this is kind of something that's been in the back of our mind. We want to do this with existing well-studied data where we know what kind of phenomena are encoded. But we want to do this in a way that's kind of optimizing for probing, not performance. So we're going to show some numbers later. They're not going to be comparable to literature on these tasks. This model is deliberately constrained because the main thing we want to do here is control for the expressive power of the probing model. So in contrast to NLI probing, which we have versions of for some of the same data sets that have been recast, if you're doing this NLI task, your model has to be able to see the whole sentence. Generally, this means training more LSTM layers on top of your pre-trained encoder. And this can mask some of the effect of this can mask attempts to probe what's in the encoder itself, because you're able to learn more contextual relationships from these additional layers. So we want to stop that. We're just going to probe the sentence itself and see what is stored in these tokens. And so specifically, the experiments I'll present, we're going to do this on the ELMO model. So sort of a to-do is to repeat all this analysis on all the models that we've talked about. I think there's some interesting stuff there, but we just haven't done it yet. And so we're just going to probe the base ELMO model. We want to know how much information about sentence structure is available. We want to know, is there interesting semantic information, or is it mostly low-level syntactic information? Does it store global information, or is it looking at just local context? And our hypothesis is that this is probably going to be mostly syntax, maybe some local type information, and we'll see what the results show later. So I mentioned trying to do all of these different tasks in a common framework. If you look at most of these structure prediction tasks, you get a graph. A graph is made up of edges, so that's why we call this edge probing. So you can take one of these annotation schemes and decompose it into edges between spans. And there have been a few recent papers that have done something to this extent. A lot of the end architectures that are state-of-the-art on these tasks are starting to look very similar. So kind of taking off that, we've recast all of this into a common format, where you have two spans, maybe one or two spans, and some label between them, and we're going to try to predict that label. So we do this for SRL. You have the predicate, the argument span. For CoRef, you can take the mentions and try to predict binary labels between them, and something similar for all these other tasks. As a model, I mentioned we want this to be constrained, so we're going to take this fixed pre-trained encoder. This gives us a representation for each token that's a contextual representation. We can pool these into span representations, and then you feed these span representations into a classifier that's going to predict independent binary labels. So in contrast to the usual kind of softmax over your label set, we want to predict independent binary labels here so that we can analyze them independently. And in terms of models, we're going to have sort of four models we want. I'm going to talk about three of them today, which is one is this lexical baseline where there's no context. We're just going to use word representations. Another is randomized ELMO, and I'll talk about that in the second section. And then the main one we're really interested in understanding with all of these is the full ELMO model, so using the pre-trained ELMO encoder. So full ELMO is going to look like this. Recall from Patrick's presentation that there's this word level representation followed by two layers. LSTM layers, and then you learn some set of scalar mixing weights on top of that. As our lexical baseline, we're going to use the same model, but we're just deleting the LSTM layers. So in order to control for any kind of differences in what the word representations are, we're using exactly the same word level representations between these two models. And then I will get to this later. So the probing suite, the set of tasks we have now, we're kind of expanding this and trying to fill things in and control for effects, but the current set is going from sort of most syntactic to more semantically oriented tasks. We have constituent labeling on PenTreeBank. We have dependency labeling for universal dependencies, entity type labeling, so taking any R and just, is this a person or a location? PropBank style SRL. We have the semantic proto-roles data set that looks at predicate argument structure, but has a much finer grained set of relations to classify. So it's a much more semantic version of the SRL type task. And then we have two versions of CoRef. There's the standard onto-nodes coreference, and there's also a small set of Winograd schema type examples. This is the definite pronoun resolution set that I had mentioned as part of the DNC suite. We're going to use the soft attention pooling to generate span representations and then feed it through a simple two-layer NLP as a classifier. So first suite of experiments is we want to know, where does ELMO help? Where does ELMO help the most? So we can just run this on each of these tasks. These are and report F1 scores. So again, everything's in a common framework, so we have the same metrics across all of these different tasks. There we go. As I mentioned, labeling variant, so we can't really compare these to the literature yet. But what we can look at is there's a pretty big variation across the task for how much ELMO helps. This is comparing the lexical baseline, where we only look at the words, to full Elmo, where we have the contextual encoder. So if we look at the top, and we've ordered these going from syntax to more semantics, we look at these pure syntax, these parsing tasks, they benefit pretty greatly. The lexical baseline is not terrible, around 75%, but this goes up a lot once you add the Elmo context. It seems like it encodes these syntactic relations pretty well. We also see this on NER labeling, that it's able to understand if something's a person, something's organization, something's a location. This is kind of something you'd expect from a language modeling objective, because if you imagine you're building up your representations in order to predict what the next word is, you might be able to fill in any one of things that satisfy one of these types, but not something from another. So that's something it's not surprising that the objective encodes this well. But as far as semantic information goes, this is pretty low level and local. Prop-bank SRL, we also see a very large improvement, but this is also known that this particular formulation of SRL is very closely correlated to syntax, particularly in the way that the core roles are annotated. Like A0 corresponds to syntactic subject most of the time, and so on. And it may be that our sort of working hypothesis, the non-core roles, we also see a lot of improvement, but these are benefiting from the same kind of type information, like this is a temporal clause and so on. If we go to the more syntactic or semantic tasks, though, we see much smaller gains, and these are not entirely purely semantic. There's still some syntactic some benefit you can get from syntax. We see that Elmo does improve performance over the baseline, but not by nearly as much. We were seeing double digits on the other tasks. Now this is down much lower. And it seems that co-ref has helped a little bit, but if we look at the very pure co-reference on Winograd, it doesn't change very much at all. So it's not capturing those very nuanced semantic relationships. And so we can look at these individual tasks. So this is looking at semantic proto-roles. One where this is a task where Elmo doesn't help that much. And it looks like there's a few of these labels. So we can, one of the things about doing these labels independently is as a binary classification, we can look at them independently and say, okay, how well am I learning this particular one? Because these data sets are nicely stratified into different classes. And it looks like, okay, actually on some of these classes, Elmo is giving us, a decent boost. But if you look at it, it's kind of inversely correlated with count. So it's kind of hard to say that Elmo is adding that much semantic information for these classes versus that it's just helping us generalize to the context on the things that we don't see very often. And if you look on the left at the classes that are most common, this is a fairly small data set. There's no benefit from Elmo over this dumb lexical baseline that sees only the words. There are a couple exceptions in the middle. I won't dwell too much on these, but I believe then that these are the more syntactic parts of the data set. This is kind of going with the earlier hypothesis. So awareness, sentient, volition, labels. But I don't think this is totally conclusive yet. We have seen, and looking at the original Elmo paper, that Elmo does help for these more semantically oriented tasks. And it's, you can't have except for maybe Winograd co-reference and these things that are sort of artificially balanced. Most semantic tasks are going to benefit from syntactic information. They're going to benefit from just generalization over lexical space. They're going to benefit from this local type information. So we can't totally rule this out, but we can try to understand a little more and say, okay, what Elmo does seem to encode a lot of syntactic information. Is it doing this in an interesting way? So Elmo, the context certainly helps. Now we want to answer the question of, okay, well, Elmo is not just a contextual encoder, but it's a learned one that's been trained on a lot of this pre-training, this language modeling data. So how much does this encoder actually benefit from the pre-training data, from the relationships it learns there, versus, say, as we saw earlier with some of the glue models, that this random encoder that provides access to context without actually giving any additional information can do quite well. It allows, it's equivalent of learning a sort of a local kernel. It lets you see nearby words. So what if we allow, we have a hypothesis that maybe some of these labels that we're doing very well on, or that the lexical baseline is poor on, actually you just need to see nearby functional words. So if you add some random encoder that kind of hashes those and lets it see those at the token level, maybe these are things that are maybe artifacts of how we define the spans will go away, And it turns out Elmo won't add so much. So we can run this. So this will be our stronger baseline. We're going to take the exact Elmo architecture. We replace the LSTM weights with random orthogonal matrices. And then we can probe this in the same way and look at the fine-grained task labels. So it turns out we do this on all the tasks. It pretty much splits the difference. This is strictly better than the lexical baseline in all cases, and strictly worse than Elmo. It's a little hard to read into sort of where in that range it falls. You can see, I don't know, yeah, here we go. So for example, on entity types, on dependency level, on these more syntactic tasks where Elmo helps a lot, you don't get as much from the orthogonal relative to what you get from Elmo. So it seems like there's a lot of information from the learn part of the actual learning part of pre-training that's very useful in these tasks. And maybe less so on some of the others, but it's a little hard to conclude that. What's interesting is we can dig down on these, on individual labels that we had these hypotheses about. So we think maybe you only need local context function words, so you should be able to get some of these things with the random encoder. So we can look at some of the things where the lexical baseline did very poorly, say on the dependency labeling task. Looking at different types of clauses that might have a marker that denotes what type of clause, looking at conjunction. Actually, it turns out the orthogonal encoder doesn't capture this very well, but Elmo does. So this is a strong sign that there's some real syntax going on here. We can also find places where Elmo doesn't know everything, and this is kind of interesting. So this is looking at the non-core roles, so auxiliary modifiers that are maybe the more semantic part of the SRL task. Most of these benefit from Elmo, and we kind of see sort of splitting the difference in the same way that we see in the tasks overall. But there's a couple cases where we actually see that the orthogonal baseline, this random orthogonal baseline, no pre-training information, performs just as well or better than the actual trained Elmo encoder. So it's possible these are, if you look at these examples, this is the direction and extent types. So it's not able to encode the semantic relation between these very well, or not significantly better than random. And you can also notice that the overall performance on these is quite low. So conclusions, Elmo seems to provide a lot of syntactic information and a lot of local type information, but it doesn't seem to provide that much information on long-range semantic relations, such as semantic proto-role types or on co-reference. The proviso, of course, is that it's still very hard to conclusively say what X phenomena is or is not encoded. You can't always perfectly disentangle things using sort of found existing data without constructing sort of a perfectly controlled target set. And it's also possible that some of the things that we can say, okay, Elmo's not learning this, but maybe this phenomenon is actually just really hard to learn, or the data is noisy, and so we want to be able to establish some upper bounds. And we have that as future work. I'll say also that one thing we do want to explore more is doing the span detection variants of these tasks so that we can sort of sanity check the encoders and see how well these are doing compared to literature models. Are some of the things we're seeing artifacts because the models are too constrained? And also this will give us sort of different versions of each task. We think that the span detection, where you identify arguments, is a more syntactic variant, but there might also be some interesting long-range relationships where you have different arguments that are competing for which one's actually attached to which one. And with that, wrap it up.
Do you think the pre-trained representations from the OpenAI paper that rely on the transformer, will those show similar trends, or?
That's really interesting. That would be very interesting to probe, because it's also a much deeper model, so there might be some interesting differences between the higher and lower parts of the model there.
Yeah, the kind of big remaining open questions on this work is looking at all of the different pre-training tasks, which is, I think, where the really interesting comparisons come in. That's all.
Yeah.
Before the paper didn't make any time before the presentation.
Our strong hope is that we will find some of these pre-training tasks that include information that language modeling is bad at, and that we can kind of fuse the two and have something that is a better universal encoder. Yes?
So you made a distinction between syntactic and semantic tasks. Subcategorization preferences, selectional preferences is something that's sort of in between, and presumably Elmo knows about that, right? Presumably the Elmo encodings know that when you, because it's doing language modeling, that when you have a verb, that eventually you're going to get an object which is appropriate to that verb, which is sort of semantic.
Yeah. Yeah, that's why I put the SRL test kind of in the middle, because it is mixing both.
Fair enough. Although there are quite a lot of sentences where you can get you can do SRL correctly, even if you replaced the words with parts of speech or something.
Yeah, so that's
so
actually
the real question is, do any of these tasks are the data sets calculated to probe whether it's using just things like word order or something closer to lexical semantics?
Yeah, so we're trying to get at that from one angle by using the lexical baseline to kind of subtract out the word prior, which is like, okay, how likely is this particular thing just to be arc2 of this verb? So the green bars were basically showing that. But we do want to attack this from the other side, and Najim's been working on noncing data where we replace the spans with nonsense, and we can see how much is it only getting from the context.
So the Elmo is trained on sentence units. The Elmo, the pre-training happens from sentence units. So it means that it sees just like relatively local context, right? When it interacts with some representation, it's always bound to the sentence.
Yes.
So could it be that the whole problem, or maybe one of the things, is that you need to force the model in pre-training task to gather much larger context, so that it ends up interiorizing some more complex representations?
Yeah, that's
grabbing local signals.
That's an interesting question, and we haven't really dug into it in this yet. I guess one asterisk I should mention is that we're doing only single sentence for now.
So maybe document Elmo grabs more semantics.
Yeah, so there's the one interesting difference between the OpenAI paper that's doing very well on the glue benchmark and the original Elmo is trained single sentence, and this OpenAI one is trained on running text that has context from nearby sentences. But we haven't really dug into this yet.
I think one hypothesis that I have is unless you ground the sentences to some semantic data, it will be very hard to capture semantics. Right? So, and that kind of data is basically absent at a very large scale.
Yes.
So, when you were considering adding these other pre-training tasks, is there any consideration for finding such grounded data? Like, I think translation is one candidate.
I don't quibble about whether translation is grounded, but unless you're talking to our other team who's doing grounded translation. But I mean, so we have like the image one and we have the CCG one, and we had, I think, similar types of maybe like relation extraction type of database grounding. Yeah.
The discourse marker one is probably the counter argument, but that is large scale.
I'll jump in briefly to mention that there was a Twitter argument that started a few days ago that's partially inspired by the topic of this workshop that led at least 20 or 30 sort of Twitter active NLP and computational linguistics faculty members to sort of chime in on the extent to which a language model can learn semantic features, and like the extent to which that's even a well-defined proposition. Should probably start
so you can go read that, and that's the answer to you. But no, I share your intuition that this is more interesting if we could probe models that are grounded to something outside of like text and language modeling, and I think we would definitely want to include it. But like, yeah, like I think it's hard to get really large scale stuff, but some of the relationship. So we'll do a very quick wrap up of open questions because we're running over. So one of our big open questions is apparently some people are still getting lists in range during pre-processing. So that's one, and then also like how to do language is hard. So other open questions. So a pretty practical one that has come up with looking at the glue results that'd be interesting to follow up on is that they're like almost running counter to this idea of general purposeness, is that different downstream tasks really benefit from different types of pre-training tasks. which is not unexpected, but then if you're trying to figure out how to build a good general purpose representation, it might require trying to model this relationship directly and then decide how you could balance your pre-training with kind of across the different types of demands that these downstream tasks might have. So I think there might be some focused research effort following up on that. Some of the more high-level ones that I think are kind of interesting as longer-term questions. So like there does seem to be some sort of like a disappointingly lack of relationship between performance on tasks and performance on these kinds of probing types of relations. So there's some maybe work to be done about like why that's the case, or what does it really mean to probe a model and expect it to contain some some information that wasn't explicitly trained to contain. Like, is that something we should be expecting these models to encode? Are we building it into the way we train the models that they are going to always rely on these types of heuristics? Like, we're not really giving them any reason not to. They're doing exactly what we're asking them to. So we should probably be unsurprised that they're relying on these heuristics. So what does it really mean if we want to train models that don't rely on these heuristics? How do they know what they're supposed to be doing when we're training them to do tasks that benefit from these heuristics? So I think there's kind of a deeper question about what we should expect, what is reasonable to expect, and what we really want with these representations. And if these can actually continue as complementary goals. I think they can, but I think it's a deeper discussion. And then even more kind of high level, it's this kind of notion of how, like this idea of probing, or idea of saying like, is my representation good, is a pretty loaded question. So I think that the notion of evaluation, which we've been really focused on this workshop with both glue and the probing tasks, of saying, how do I know my representation is good? We really have to come up with some observable behavior that we say, this is what a good representation can do. So generalizability is a really obvious one, with good practical motivation, and these kinds of probing phenomenon are really good evaluation from kind of an interpretability standpoint and like a intuitive standpoint of what language should contain. But there's this notion that there's always tasks we don't know that exist, and we need to be able to generalize to a task that doesn't exist. We need to be able to generalize to a speaker that doesn't exist, or to some probing phenomenon that might not exist. It might be some one-off thing where the model gives the wrong behavior. So it's hard to say now how we know that a representation will be good in those future cases. And so knowing what a representation knows, and knowing when you've when you've converged on the right one, might not be an answerable question, but I think in the notion of building general purpose representations, that's what we're butting up against. So it's worth having that discussion, maybe not in our question discussion, but offline. And
all right, let's steal 2 more minutes of your time and then hand the floor back to Sanjeev. Just a couple of things that I wanted to add. With our work on Reddit, which showed that Reddit is a decent pre-training task, but not sort of by any means competitive for the best thing we found, we proved Ray Kurzweil wrong. If anyone wants to know if JSOL has anything to do with Ray Kurzweil. Also, I reported there were 5 bunny sightings reported on Slack. We had 1 more during the break. So just to repeat the takeaways. We built a bunch of stuff. We built a pretty large library of reusable sentence encoders, many of which are hovering pretty close to the state of the art. We built a fast modular software toolkit for the training analysis of sentence encoders with implementations of about 70 tasks built in, and a library of human-annotated data sets for the analysis of NLP model behavior. What did we find out? Language modeling works as a pre-training task according to our sort of practical metrics, as well as anything else. Doing multitask learning on top of that can get you some additional mileage. But different tasks benefit from different kinds of pre-training, and even many of our very good models who are trained with a lot of data, a lot of resources, are still really systematically failing at a lot of pretty straightforward, pretty obvious aspects of English syntax and semantics. So a lot of work left to do. What's next? We've got a bunch of stuff that's still going. Experiments, translation in Elmo, some newer, bigger learning curves, some sort of final questions on multitask learning methods, and we're scaling up some of our experiments to larger, bigger, slower models. We're cleaning up the code base, and we've got 3 papers that have outlines and titles and deadlines, and a couple more that are still ideas. So thanks to everyone for listening to our massive 3-hour talk. Alison Ettinger, just to give some credit, was sort of an early advisor to the team. Anpreet Singh, Julian Michael, Felix Hill, and Omar Levy did a lot of the work behind Glue. And a few people who were on the team but didn't speak today, Ben Venderme, Tal Linzin, Vestoyanov, and Dipanjan Das, and actually Edward Graf as well, had a name on the slide that didn't come up here, so all of them contributed to the results you saw as well. Thank you. We'll have to take any lingering questions after that.
No, you can are there any questions for the whole team? You can spend a couple of minutes.
So, are there anything that you would remove from Glue or add to Glue after this workshop?
My engineer hat on, I would remove WNLI. It's just this source of complete random garbage noise. But with my analysis hat, I think it's really good hard data. I think that
it's not random garbage noise. It's the one that's preventing you from relying on these heuristics.
Exactly.
So it's probably the best test. I would say remove everything except WNLI.
Yeah. There'd be some merit to adding sequence style tasks, but I think that would also make it a lot harder to use. So we can go back and forth on that. Any more, Joe?
Any more questions for Sam? Yeah, one more here.
So in a lot of your programming experiments, it seems like your random baselines actually do pretty well, at least from what I understood of it. I'm kind of wondering if you're just rediscovering that like random features are actually not a terrible idea, rather than like random is actually terrible and should be fixed. I'm kind of wondering if you're just rediscovering that like random
I'd argue that yes, we kind of are. That I think we've had this result since day one. That random LSTMs are pretty good encoders. There is literature on this going back pretty far. Echo state networks, reservoir computing. But yeah, sort of we've seen really impressive results with things like Elmo, and it's this question of sort of how much of this is just using a big LSTM, how much of this is actually running something.
And so like on the probing experiments, random does well, as in it does, like some of the trained models do worse than random, but random isn't doing well, right? So it's not actually capturing these phenomena. And so what we're seeing, which I think is intuitive and useful, is that pre-training can learn the wrong heuristics and the wrong devices that get you worse than random, or it can help, right? But it's not that random is actually capturing the phenomena. It's still performing at random on these tests.
I didn't mean that random is doing well. I mean it's doing very well compared to trained models.
Right, which is I think an interesting result, which is like pre-training can hurt you because it can prevent, or it can cause you to learn certain types of heuristics and exploit them that aren't actually ones you want to be learning, right? And that's random.
Because I was referencing that the idea of you could just have a big encoder that's mostly random and linear on that.
Right. As opposed to pre-training on a task that actually makes that classifier worse, suggests that pre-training task was hurting by encoding some non-useful features.
That method of starting with random has been called extreme learning machines, I think, in a paper a few years ago.
All right. So if there are no more questions, let's thank Sam and team again. So this has been an intense day and a half. I hope everybody enjoyed the presentations. I certainly did. And I wanted to make some concluding remarks, which I might do without slides if this thing doesn't come back up again. No, sorry. So whatever okay, should I wait another minute to see what happens? This computer has recognized that it's connected to something. The display is changing. Right, you know what? We can do it without slides. Don't worry about it. Yeah, okay. No, it's okay. All right, so firstly, I hope you all had a good time listening to all these people. I know they had a good time doing all the research. So let's first maybe give a hand to all the workshop team. Oh, yeah, all right, good. So this is just to remind you about what we've been doing for the last day and a half. So what I did is on Wednesday night, when I was getting ready for these presentations, I asked the team leaders to help me summarize what the teams had accomplished, and I made some notes. And I thought I'll give this as my recap of what's happened. And I realized after listening to the teams that they've actually done a lot more than what I thought they had done. So I'll still go through my points, but maybe they're incomplete and they'll need to be revised in time. So first we heard from Takaki and his team. They did a lot of nice work on sequence-to-sequence models for speech recognition. I think of their team as working on, like, when you have a fair amount of data, can you improve the architectures, make the sequence-to-sequence models better, integrate language models, and so on and so forth. They have this minimum word array training folded into it, and so on. In the medium data case, they looked at multilingual systems, and I think they were trying to do, and train with multiple languages together. And then finally, in the almost no data case, or the zero resource case, they were looking at the cycle consistency type ideas. So I thought all that was pretty nice. Nothing, no bombshell was dropped yet, but I think we are getting to the point where we understand these models better, and hopefully we can sort of do more fun things with them going forward. And of course, the nice thing is everything is in the open source, ESP.NET, so people can play with these things later on. Lucia and her team, they worked on grounded sequence-to-sequence transduction. They had these 5 little sub-teams, if you will. I thought that the speech transcription and the speech translation, they called it ASR, SLT. That was one task where it was fairly clear that multitask learning helps both tasks, they both work better. I thought what Florian and company talked about in terms of summarizing video content, I think we're still struggling with names. They're not teasers in the sense movie trailers are teasers. They're not summaries in the sense abstractive summaries are done. They're more like a description of what's in the video. So I'd call it a descriptive summary, or maybe a descriptive gist of the video. The region-specific MP worked nicely. You could see that with some supervised grounding or supervised attention, you could get nice improvements. Then there were a couple of exploratory tasks with the multi-view learning. I think there was some, what I found intriguing, for example, was that with the speech, just speech, no transcription, just a speech signal, you could retrieve something that resembled the translation of that speech, which was sort of amazing if you think about it. So you have multiple views. They do end up putting similar things together, which is surprising but nice to know. And then the multitask learning, there were these ideas about a shared representation space. I think Z space is probably a good idea, a good name, I like that. And then the mutual projection network. So that's a nice, and also the data set, the how-to data set is really nice. It's huge, and I think we maybe annotated half of it. The rest of it could be finished at some point, and it will become very useful for a lot of things. So keep an eye on that going forward. I'm sure there will be lots and lots of papers written on it in the future. And then finally, Sam's team, the main message I got was that Elmo is still bigger than Cookie Monster, although Cookie Monster sounds like a big name. And of course, we already saw signs that capturing semantic similarity, if it's crucial to your task, Elmo is still not there yet. But I also thought that even though Sam underplayed it a little bit, being able to train smaller models with less data, being able to train 3 GPU days instead of 8 GPU months, I think is actually a significant accomplishment. So I think we should not sort of minimize that. And they looked at many tasks that were good for pre-training. And it's not surprising to me that task-specific pre-training works well, because I think these models still, they still copy what they're taught. So they're not deep in the sense that we think about human brains as deep. So I wouldn't be surprised if the long-term lesson is that, well, pre-training only helps so much. In the end, you have to do task-specific training anyway. And so that's the real way to solve these problems with machines we have today. And I think, Sam, you called them the graveyard of pre-training methods. They still teach the models interesting things, I thought. And so the probing task showed that. And overall, it was a nice deep dive into what these sentence representations are doing. This is the kind of understanding of our neural models that is still missing, and we need to do more of it going forward to know how these things will work out. Okay, so all this was nice and good. None of it would have happened but for these good folks. So let me take this opportunity to thank all our sponsors one by one. So Facebook, I think Darren's back there, Darren Green, Christian, Eduardo's there, Catherine, and Wes, are you online? You should be. This is your team's work that you're seeing this morning. Hopefully Wes has woken up and is seeing it from the... Anyway, so this has been a nice team, nice support for us. Thanks, everybody. Amazon, Rohit Prasad is not here. His team has always been a consistent supporter, but I think Hassan, where is Hassan? Hassan's over here, and Katrin back there, and who else is there? I think Hari was here yesterday, Harish was here. There you are. Yes, thanks guys. By the way, also I'm very grateful that you guys actually took the time to come here. And Bill, yes, Bill's there. Because it's one thing to just say, oh yeah, here's some support for the workshop. It's a whole other thing to say, I care enough about it that I'm going to come spend 2 days, listen to what you did. I'm going to follow you online. I'm going to tweet back to you about things you're doing. It's really nice. Google has been supporting the workshop for 10 years now. I think this might be the 11th year at this point. Mikhail, Johan, I think, what should I thank? Fernando, Corina, the whole gang. Dipanjan is here, Slav. So thanks everybody. Again, thanks for showing up in large numbers to listen to us and to work with us and formulating the problem and working on them. Like I said, one of the nice things about the workshop was that when I looked at the senior participants, about 40% of them are from industry. So this sort of reassures me that yes, we are working on relevant problems and important problems. Microsoft, again, has been a consistent supporter. Jinyu is here, but there were others involved through the planning process, and it's been very nice. Mitsubishi Electric and Mitsubishi Electric Research Lab and the company itself. Anthony is here. And of course, we had others visiting through the summer, and Takaki himself, of course. And there's Chiori. Oh, maybe, there you are. Thank you. So thanks for visiting. Thanks for coming and joining us. And finally, we have a new friend, M-Modal. Where is Thomas? Yes, and the M-Modal folks. So thanks, and keep joining us. Next time, we want you in a team, not just visiting us to listen. So let's do that. So again, a big hand to the sponsors. And finally, I get here and pretend that I did all the work of organizing, but in reality, a lot of it happens due to other people, and you've seen them around all through the summer. Najim, of course, makes himself very visible, but Yanda, where is Yanda? There you are. So Yanda and Najim have sort of been workhorses. They've pulled everything together, and there is a person behind them who really needs a serious, big thank you from all of us. So. And she's not here because right now she's organizing the next part of this event. That's Ruth. So again, Ruth. Really, this center, this whole workshop would fall apart if Ruth weren't here. So absolutely, Ruth is a key person. Yeah.
And she'll likely be there at least the start of the dinner tonight.
Oh yes, exactly.
So please do thank her.
Yes, when you see her at dinner, please make sure you go up to her and thank her, because she really does magic. Yes?
To publish all this wonderful work, just a little commercial, IWSLT deadline is just end of August. And for speech translation, it's actually a wonderful forum to publish some of the innovative work.
Yes, so again, IWSLT, the deadline is coming up.
Rouge in October 29th and 30th.
All right.
Rouge in Belgium. Beautiful.
Yeah. Okay, so other than that, I have a couple of quick housekeeping announcements. After we break up from here, we have a special lunch for all the student participants of the workshop and others who signed up. And that is upstairs on the 3rd floor. And this is a chance for our industry colleagues to meet with the students, to figure out what they're doing, maybe lure them to come do internships or whatever else, and so on and so forth. So student lunch upstairs in Hackerman 320, as soon as we finish here. Next, after lunch, we have a couple of very nice talks from our visitors. So people like, this is one of the things we like to do as academics. If somebody visits you, you pick their brains. You don't just let them come hang around. So Chiori is going to give us a talk about the Dialogue Systems Technology Challenge, and then where is Marcus? Marcus. And Marcus is going to, Marcus just defended his PhD thesis, congratulations. And nice work on using language encodings to do multilingual linguistic training. So both those talks will also be upstairs in 320 right after the lunch. So we'll see you there. And one last thing, Ruth, again, although she's not here, she's still running the show. So if you see my hands moving, you know who's pulling the strings. So I have to make a housekeeping announcement. We'll do team photos. Yenda has taken some terrific pictures, but he says that to get a really nice group photo, you need a special lens, and he doesn't have that. So we're going to get a photographer to take team pictures. So all the 3 teams will take them at dinner, but we'll do it before it gets dark. So try your best to be there on time at 5:30. Otherwise, we'll have to shop you into the team photo later. So please, everybody at dinner at 5:30. All right?